Welcome to the Mastering Python video course. In this video course, we're going to start with the fundamentals and then work our way up to talk about more powerful and advanced techniques of Python programming. I am Daniel Arbuckle, and I'll be your presenter for this course. I began using Python approximately 20 years ago, and have used it ever since for both research and professional work. This first video is a quick sneak peek of the course as a whole, where we'll discuss the topics that we will be covering throughout the course. In the first section, we'll look at how to get started with Python. We'll first walk through downloading and installing the Python interpreter and standard library. Then we'll take a look at the Python interactive shell and running Python programs from the command line. Next, we'll take a look at pip, Python's tool for installing third-party libraries, and see how to find those third-party libraries using the Python package index. In section 2, we'll talk through creating an empty Python code package, and then extend that by adding code modules to the package. We'll then take a short detour to talk about how to import package modules into each other, and see how to add data files to the package. In section 3, we'll talk about best practices for Python programmers. These are things that you don't have to do, but the weight of experience says that they're good ideas. Here, we'll talk about Python's widely accepted code formatting standard, we'll see about using version control, virtual environments for developing code, and how to format inline documentation and integrate that documentation with testing. In section 4, we'll put the theory on the back burner and cover the practicalities of creating a command line program. Here we'll talk about turning a package into a program, handling command line arguments, interacting with the program's user, how to start other programs from within our Python code, and finally how to start our program from a graphical user interface. In section 5, we move on to more advanced topics. We're going to take a look at how to run our code across multiple CPUs or CPU cores. We'll examine the concurrent.futures package in the Python standard library, which provides a simplified high-level interface for launching and working with background worker processes. And then we'll look at the multiprocessing package, which provides a lower-level interface to multiprocess programming. In section 6, we're talking about asynchronous I/O and cooperative threading with coroutines. We'll explain the difference between cooperative multithreading and multiprocess programming, then look at Python's built-in async.io package, async.io's feature class specifically, how to force synchronization back into existence in those places where it's really needed, and finally, we'll look at using the tools we've covered in the prior videos to communicate across the network. In section 7, we'll look at several ways in which Python code can rewrite or change the meaning of other Python code. We'll look at function decorators, function annotations, class decorators, metaclasses, context managers, and descriptors. We'll wrap up with section 8, in which we'll be looking at how to construct a suite of unit tests for our software. We'll talk about the principles of unit testing, using Python's built-in unit test package, and using unit test's mock module to help control our test environment. Then we'll talk about unit test's test discovery tool, and wrap up with a discussion of Nose, a third-party tool that adds a range of useful testing utilities. The videos in this course are organized more or less in order from fundamental to complex. They're not tightly bound to that order though, so feel free to skip around if you wish. This course is divided into two major parts. For the first several sections, there's nothing you need except an interest in the topic. We'll cover basics that will help you get started. The later sections are more advanced. At a minimum, you should be comfortable with the content of the basic sections before tackling the advanced ones. And even so, practice and experience with Python will be helpful. Join me in the next video where we'll be downloading and installing Python.
The primary purpose of this video is to make sure you have a working Python development environment. That's going to involve looking at which version of Python do we want, setting up environment variables, and then double-checking to make sure that the environment actually does work. Before we can really begin working with Python, we need to make sure we've got the language interpreter and libraries properly installed. The first step of that is to decide which version of the language to install. There are currently two common variants of Python in use. One of them is Python version 2.7, which is the final version of the Python 2 series. The Python community has promised to maintain version 2.7 indefinitely with bug fixes and backporting some new features, but primary development is happening in the Python 3 branch. Python 3, which at the time of this recording is in version 3.4, with version 3.5 coming soon, is the active branch of Python. During the change to version 3, the language and libraries were changed in subtle ways, as you can see by comparing these two code snippets. On the left is Python 2. On the right, you see equivalent code in Python 3. You're free to pick whichever version you want, but I recommend Python 3 because that's the version that I'm going to be using for the examples throughout this video series. Now that we've picked a version, let's install it. If you're a Windows user or just like doing everything for yourself, go to the python.org, download the appropriate package, and install it. Otherwise, use your operating system's package manager to install the version you want. If you've used a package manager, this next part is probably already done. Otherwise, we need to make sure that the Python programs are able to run from the command line. On Mac OS X and Unix-like operating systems, all we need to do is add a line to the profile or bashrc file in our home directory. That line is shown on the screen at the moment. Windows is only slightly more involved, involving 4 steps that basically add up to the same result. In each of the examples on the screen, path to Python programs is not literal. You need to choose the actual path where you have your Python programs installed there. Once we've got the path environment variable set, we should be good to go. To check that, open a terminal window and type Python, then hit enter. If you don't know how to open a terminal, don't worry, we'll talk about that in more detail in just a moment in the next video. If the Python interactive shell starts up, we type Python into the terminal, we're good to go. If it doesn't, go back and double check the changes that we made to the path environment variable, because that's the piece that tells the operating system where to find the programs. So, in conclusion, you're free to choose whichever version of Python you want for your own usage, and even here, but I suggest using version 3.x because that is the version that I will be using. If you need Python version 2, version 2.7 has long-term support. It's not going to go away. You can use it for as long as you have the need. Environment variables are how the operating system finds out where to find the Python programs. They're the integration between Python and the operating system. In the next video, we'll learn how to perform quick experiments and harness Python's help function. Now it's time to take a look at actually using the command line and the interactive shell. We're only going to briefly look at the command line just now, because all we need it to do at the moment is to start up Python. Then we're going to take a longer look at the Python interactive shell, and then we'll see as we're working, hopefully, and then as we're working, we'll see what we gain by using these interfaces. Text-based interfaces are not much to look at, but they're highly useful to programmers. They provide a quick and easy way to interact with programs while they're in development, experiment with code, which is, after all, text, and access documentation. How you open a command line window depends on the operating system you're using. On Windows 7, open the Start menu and type CMD into the Run box. On Windows 8, press the Window key and then type CMD, hit Enter. On Mac OS X, run Applications, Utilities, Terminal. On Linux or other Unix-style operating systems, the precise mechanism for opening a command line window varies, but they all have the ability to do it and display it rather prominently. Look for the words Xterm, Terminal, or Shell. Now that we've got a command line, we're going to go straight into the Python interactive shell. We type that by typing Python into the command line window. If we have multiple versions of Python installed, and we want to interact with a specific version, we can explicitly choose the version we want from the command line by typing the version's name with a version number. For example, if we type Python 3, we'll explicitly start up some version of Python 3.x. Here's where the fun really starts. When we see that triple greater than prompt, we can type in any Python expression or statement and see the result immediately. That's incredibly useful because it means we don't have to remember every detail about how specific functions work, what class members are called, which exceptions are raised under which circumstances, and so on. Whenever we're unsure about something, we can just open up an interactive shell and find out. So, for example, let's imagine we're working on an application that uses Python's set data type. And we're unsure about what exception gets raised when we try to add a set to itself. We could go digging through the documentation, but it's quicker and easier just to create a set in the interactive shell and try adding it to itself. Right away, the system tells us that adding a set to itself raises a type error exception. Sometimes running a quick experiment in the interactive shell is absolutely the fastest way to get the information we want. But documentation is nice too. Fortunately, Python has a very good documentation system that we can access straight from the interactive shell by calling the help function. We can pass any object as the parameter of the help function, and it will print out that object's documentation for us. So, if we want to find out about the functools.wraps function, we just pass it to help and read all about it. The help function can also take the name of the object you want to read about instead of the object itself. That can save us the time of typing the import statement in the interactive shell. The difference is that the parameter is a string, not an expression, that evaluates to the object we're interested in. However, since it's a string that generally contains that same expression, the difference is just whether you want to put quote marks around it or actually import the thing. So, the operating system command line gives us easy access to Python and to our own programs written in Python. The interactive shell is a great way to perform experiments, and it also provides us with access to Python's built-in documentation system. In the next video, we're going to look at another command line tool called pip, which allows us to install and update third-party code libraries and programs. We're going to look at Python's built-in package management tool, pip, which allows us to install, uninstall, and manage third-party Python source code and utility packages. We're going to see how to install into your personal package library as opposed to the system's package library, and we're going to see about managing and removing installed packages. And so it's back to the command line for us. We're going to see how to easily install third-party code from the extensive Python package index. While Python comes with batteries included, meaning that the Python standard library that's already installed contains a wide variety of very useful features, there's still plenty of things it doesn't do. Odds are, though, that somebody somewhere has already invented the wheel for you. And if so, you can probably find it in the Python package index. Python 3.4 and later are installed with a tool called pip, which can interface with the Python package index and automatically find, download, and install Python packages. If you already know the name of the package you want, and you have permission to write into Python's library directory, then this relatively simple command will get it fully installed and ready to be used. In that example, Z was the name of the package we wanted to install, and you would replace it with the name of the package you actually want to install. However, in this case, the install did not actually happen because, as I mentioned before, it requires that you have access to write to Python's library directory, which I do not have. However, every user has a personal library directory as well, and only a small modification of the command will install a personal library directory instead. To tell pip that you want to install into your personal library directory, just add --user to the command right after the word install. Pip can do more than just install packages. It can also give you a list of currently installed packages, upgrade currently installed packages to the newest version, and uninstall packages that we don't need anymore. In short, it's a complete cross-platform management tool for Python packages. Some Python packages require that you be able to compile extensions written in the C programming language to install them, but fortunately that's becoming rare. Normally, if a compiled extension is required, pip will be able to find and install the proper precompiled version automatically. The majority of available packages are pure Python anyhow. Pip has a great many more options than command line switches, but what we've seen so far covers the common situation as well. If you want to dig into it further, pip's help command will give you the details. For example, this command prints out all the information you could possibly want about the pip install option. In this video, we figured out how to install third-party packages that cut to the chase and make life much easier. In the next video, we'll see how to sift through the Python package index to find the packages that we actually want. We've talked about installing packages from the Python package index, but what if we don't have a specific package we need to install? What if we just need a library to help us get the job done, but don't know specifically which one we need? Well, as the name implies, the Python package index is actually an index of packages, which classifies them according to a number of parameters. We can search the available packages in a number of ways. The index is conveniently hosted at pypi.python.org. Perhaps the most useful way of accessing the index is to simply type keywords into the search box on the web page and see what it spits out. If we ask it to search for async.io, we get back a collection of package names that have something to do with the names are, of course, links to each package's detailed description on the index, which we can use to decide which package best suits our needs. There's another way of accessing the index that is often nearly as useful as keyword searching, and sometimes even more so. The Python package index supports browsing through its index of packages by category. You can start browsing by clicking on the Browse link in the menu to the left, which brings up this list of different categories. From here, you can select one or more categories by clicking on them, and be shown the list of packages that fall into all of your selected categories, if the list is short enough to be useful. If you don't get a list of packages, it's because the list would be so long that it wouldn't do you any good, and you should select more categories to narrow it down. If a category disappears from the list while you're selecting, that means there are no packages that are in all of your selected categories, and in that one as well. Of particular note here are the natural language categories. Python is not only written in English, and not only used by people who prefer that language. Some packages have good support for other languages, and this list is a good way to find them, whereas keyword searching might not pick out that kind of detail. If you don't want to fire up your browser to go searching through the index, you can do it through the command line through pip. This command performs the same search that we did earlier through the web interface. Doing it this way is often faster, but as you can see, it only provides us with the name and a brief description of each package. This is perfect for getting a quick reminder about what a package is named, but not so good for more in-depth research. Finally, a quick note about legalities and licenses. The vast majority of packages in the Python package index are under open source licenses, as certified by the Open Source Institute. That means basically that they can be freely used and distributed to other open source projects. In most cases, the licenses are more liberal than that, allowing you to use the software as part of your project even if you don't open source your own code. Most does not mean all, however. Some of the packages are not on certified licenses, and some of the OSI licensed packages are not usable in closed source projects. If you're going to be distributing your software, take a moment to make sure that the licenses line up with your goals. In this video, we've seen how to navigate the Python package index and find exactly what we need. And that wraps up Section 1 on setting up our environment. In the next section, Section 2, we'll begin actually writing Python code.
Section 2, Making a Package. 2.1, Creating an empty package. We're going to look at creating a folder to contain a package, making sure Python recognizes it as a package instead of just a folder, and making sure that Python can find the package when we ask it to import it. Very simple Python projects may consist of a single code module, but normally they are multiple modules combined together into a package. A package can contain as many modules as we need. Packages start their lives as folders on the file system, which means we can make them just as we would any other folder. If you prefer to use your operating system's file browser to make folders, that's fine, but I usually use the command line. There are two things that turn a regular folder into a package. The first of those two things is where it is. Python only looks in certain places for packages, and if your folder isn't in the right place, Python won't notice it. The sys.path variable that I've just displayed on the screen contains a list of all the places Python will look for packages on my system. It will change on other systems to reflect the differences between local installations. Notice that the first entry in the sys.path list is an empty string. That stands for the current working directory. For those of us using the command line, the current working directory is just the folder we're currently in. We can change the current working directory with a cd command. The fact that the current working directory is on the path is convenient during development. It means we can just set the current working directory to the place where we're doing our development, and all of our packages become available, at least as long as we use the command line to launch Python. The second thing that turns a regular folder into a package is the presence of an init.py file. Though not strictly necessary since Python 3.3, an init.py file marks the folder as a package, which makes it load more efficiently and also gives us a place to put information and code relevant to the API of the package as a whole. Well, it's quite common that an init.py file is completely empty and serves only as a marker. There's one language feature that won't be supported unless we add a little code to the file. That feature is the ability to import all of the package's modules using the import star syntax. If we want Python to be able to do this, we have to tell it what it means by all of the package's modules. To do that, we add the module names to a list called all in the init.py file. You may be wondering why we need to do this manually rather than Python just scanning the file system for module files. There are a couple of reasons. First, Python tries not to make any assumptions about whether file names are case-sensitive or not. On some operating systems they are, and on others they're not. Module names are variables, so it's better if they originate within the source code rather than depending on something external that might change. The second reason for doing this manually is that importing a module makes code execute. Imagine we have a package that plays soundtracks. In addition to the general-purpose code, we also have a bunch of modules that handle audio output on various systems. It's quite reasonable for our users to do an import star to bring the package API into their module, but we don't want all of the output modules to load, just the ones appropriate for the system we're running on. Trying to load all of the others would likely trigger an exception in the user's code. The way the all variable works now, we can exclude the output modules from the import star and get the best of both worlds. Alright, let's make sure that Python is willing to import our demo package. So the package folder can be created from the command line or from whatever graphical interface you find most comfortable. If the folder is in one of the places Python searches and has an underbarred init.py file, it's a package. We can support from package import star if we put a double underboard all list inside of the init.py file. And we can check that the package is valid by using the Python interactive shell to try importing it. And then we'll move on to how to add source code modules to a package in the next video. 2.2, adding modules to the package. We're going to look at choosing file names for our modules, as well as the difference between normal packages and namespace packages, and the difference between a package's structure and its API. Python modules have the same name as objects that they have as file names, except that without the .py suffix. That means the file names of Python modules need to be valid Python variable names, and also they should use letters and symbols that are reliably available across different operating systems. As an example, module names should not start with a number because Python variables are not allowed to start with numbers, and should not use capital letters because some common operating systems don't differentiate between file names containing capital letters and file names containing all lowercase. As long as we stay within those guidelines, remember to use a .py suffix, we can name our modules anything we please. So we just pick a file name and start writing Python code into a file with that name in the package folder. That simple scenario is also the common case, but there's another possibility. As we've mentioned before, starting in Python 3.3, it's possible to have a package folder that doesn't an init.py file. Leaving out the init.py means we can't support import star, or other tricks with init.py that we'll discover as we go along. There's more to it than that. When init.py is missing, the folder becomes a namespace package. When Python is importing, it combines all of the namespace package folders it finds that share the same name into a single logical package. That behavior then means that, while choosing the module file name still follows the same rules, we could potentially place that file into one of any number of namespace package folders instead of into a singular concrete package folder. What do we gain from that? Often nothing. As I mentioned before, packages with an init load faster, and in many cases the extra abstraction of namespace packages doesn't buy us anything. There are cases, however, when we want different parts of the same package to be distributed or managed separately, and when we do, namespace packages address that need. For example, imagine again that we are working on a package for playing soundtracks. If we make a namespace package for audio codecs, each codec can be installed and removed individually using pip or the operating system's normal tools. On a slightly different topic, now let's talk about the difference between how a package is structured and the interface it should present for use by external code. For the convenience and sanity of ourselves as package developers, it's often best to break up code in a package into many different modules, each containing a selection of conceptually related code. That is the package's structure, and as a rule of thumb, whenever we think we might want to break up the code into more modules, we probably should go with that impulse. On the other hand, external code calling on our package is best off when it can take advantage of our code with just one or two import statements that bring in a small number of functions or classes. That is the package's interface, and as a rule of thumb, it should be as minimal as possible while preserving full functionality. Fortunately, we can have our cake and eat it too. We can divide our code up however we wish, and then import the most useful elements into init.py, which will then make them part of the package's root namespace. If all its init.py is import statements, we don't need an all variable. An import star will grab the contents of the init.py file, except for variables starting with an underscore. However, if we define or import anything into init.py that should not be part of the public interface, we can use the all variable to narrow down and control what we export. Just remember, if we have an all list, it needs to list everything that is part of the package's interface, whether a module, class, function, or variable. The rest of the modules in the package are still available to be imported explicitly. We're just making it convenient to access the parts that are most likely to be useful outside of our own package. Now that we have a good idea of how to name our modules, where to put them, and they become part of our package, and how to give our package a convenient interface, so file names should be valid Python variable names and lowercase. Code should be broken up into as many modules as it takes to keep it organized properly, but the parts of the code that are most useful for a code outside the package can be imported into the double underboard init.py file and added to a double underboard all if we're using it to make them part of the API. Since Python 3.3, folders that don't contain a double underbarred init.py file are namespace packages, which have slightly different properties from normal packages. but have their uses. We'll move on to looking at how to make the modules in a package interact. 2.3, importing one of the package's modules from another module in the same package. So we're going to look at relative and absolute import statements, and what to do when two modules import each other. So we're going to look at how Python 2 and Python 3 have slightly different rules for how import statements find packages. When we're importing one of a package's modules from outside the package, there's only one sensible way that it could work. We tell Python which package and module we want, and either finds and imports it, or raises an exception if it can't. Simple. When we're already inside a package, the situation is more ambiguous, because import module could just as easily mean look for the module with that name within this package, or look for the module with that name on the Python search path. Python breaks this ambiguity by defining import name that a package or module called name should be searched for in the Python search path, and by giving us a way to specify a relative import if we'd rather have it look just within the current package. We can specify a relative import by putting a dot in front of the name of the module we want to import. When Python sees that, it will look for a module called module in the same package as the module our code is running in. Often we only need one or two objects from another module. It's more convenient to import those objects directly into our global scope than it would be to import the module as a whole and access its contents as attributes. Python lets us do that with a slight variation of the import syntax. Finally, sometimes we want to rename an object within our scope as we import it. We can do that by modifying our import with the as keyword. In this example, even though the object is called foo in the module named module, in our current module, it's named bar. Before we move on, let's take note that Python 2 used a different rule for deciding where to find imported code. In Python 2, it first tried to find the targeted import within the current package. Then, if no matching module was found there, it went out and looked for it on the search path. That approach usually did the right thing, but occasionally caused problems due to the ambiguous meaning, and it meant that we couldn't have subpackages or modules that shared the name of anything in the standard library or other installed packages. So this behavior was changed in Python 3. There's something that might trip us up when we're importing a module that shares the same package. Sometimes, in a module that doesn't import, the imported module wants to import the original module. This is called a cyclic dependency. When we import a cyclic dependency, we'll almost always get an attribute error exception, as in this example. That happens because when we ask Python to import the first module, a.py, Python immediately creates a module object for it and begins executing the code in the module. That's fine, except that when Python gets to the import statement for the b.py module, it pauses running in a.py, leaving it not fully initialized, and proceeds to execute the code in b.py. Even that normally isn't a problem because Python will come back and finish the initialization later. However, when the second module asks to import the first module, Python just hands it the already allocated and not fully initialized module object. When the second module tries to access the variables stored in the first module, many of them will not have been created yet. Hence, the attribute error is raised. There are two common ways to address this problem. The first, and usually the best, is to break the cycle by taking some of the code from one of the modules and moving it into a third module. Both other modules can import without causing a cycle. In this example, if we move the A class into its own module, there would be no cycle and all would be well. The other way to address this problem is to move the import statement that causes the cycle. If we move the import statement down until it's below all of the variable definitions that are needed by the other modules in the cycle, the module will be initialized enough when it's imported by the other modules. Python will still come back later and finish the initialization. So relative imports look like from .import module or from .module import variable. Absolute imports look like import package.module name or from package.module import variable. If two modules import each other, move some of the code to a third module, or import one of the modules at the bottom of the other. Now we have a pretty good handle on importing within a package. Let's move on to adding data resources to the package. 2.4, adding data files to the package. So we're going to look at where to store the files that we want to include in a package, and the package util.getData function for retrieving that information. We're also going to see how to handle the situation when our files contain text instead of binary data. Alright, if we're going to be adding data files to the package, where should we put them? Really, put them anywhere that's convenient within the package folder. But it's often a good idea to create a subfolder specifically for holding data files. That keeps data files separate from source code and generally makes working with them a little easier. You should note here that data files that are part of a package should be assumed to be read-only. There are many reasons that might cause the files to not be writable at runtime, so if we want to write data to a file while our code is running, we need to pick somewhere else to store it. Only files that do not change are appropriate for inclusion in a package. So, that said, all we have to do to include a data file in our package is to drop it into our package folder, and then access the data with the getData function from the package util package in the standard library. The getData function takes two parameters, the name of a package we want to get data from, and the relative path of the data file inside that package, using forward slashes to separate path components. We pass those two pieces of information, and it returns a bytes object to us containing the contents of the file. If we want a text string instead of just bytes, that's easily done. We need to apply the proper string decoder to the bytes object, and we'll get back a Unicode text string. In this example, we used the UTF-8 decoder. The technique works even if our package has been compressed into a zip file or otherwise hidden away because it uses the same underlying mechanism that Python uses to load module source code. If Python can find the source code, it can find the data file as well. So data files should be stored in a subdirectory of the package. Using package util.getData, we can retrieve the contents of the data files. The package util.getData function will work even if our package has been zipped up or otherwise stored through a different and unusual module loader, because it uses that module loader to find the data just as it would to find the Python source files. If the file's contents are text, we can use bytes.decode to transform the file's content into decoded text. That brings us to the end of our section about making packages. The next section covers a number of best practices for Python programmers, and then we'll move on to master some of Python's more esoteric features. Section 3, Basic Best Practices. 3.1, PEP 8, and writing readable code. We're going to look at spaces and tabs, as well as Python's expected code layout and naming conventions.
PEPs, or PEPs. PEPs, which stand for Python Enhancement Proposals, are the documents that establish standards within the Python community. Most PEPs describe new features for Python or Python's standard library, but a few of them are more nebulous. PEP 8 is one of those. It tells us what the Python community considers to be well-written, readable code. The very first rule that PEP 8 introduces is that the rules of PEP 8 should only apply when they make our code easier to read. If we're working on a project that was already written to a different coding style, we should use that project style for new code. If we're writing code where the PEP rules don't make sense, or somehow make the code harder to read, we should ignore them. As Guido van Rossum, the creator of Python, has noted, code is read more often than it is written. It should always be written in a way that promotes readability. When programmers read code, we look at how it's indented to tell us how code blocks are nested. But most other programming languages use actual symbols to tell the parser where the blocks begin and end. Encoding the same information in two different places is a violation of the basic best practices of programming in any language, so Python omits the beginning and end block markers and uses the indentation to inform the parser as well as the programmer. There is one problem that arises from that, though. There are different ways of encoding indentation in a text file. We could use space characters or tab characters, or even a combination of both, or even some other non-printing characters from elsewhere in the Unicode spectrum. The code we're looking at right now mixes spaces and tabs, which in Python 2 is valid but a terrible idea, and which in Python 3 is a syntax error which raises a tab error exception. I've configured the editor to highlight tab characters, so we can easily see which indentation comes from spaces and which comes from tabs. To see why mixing tabs and spaces is of no good, even when it's allowed, all we have to do is change the tab width. Even though the indentation looked good before, now it's clearly wrong. And to the compiler and parser for Python, nothing has changed at all. There's no ambiguity if all the indentation comes from tab characters, so using only tabs is valid even in Python 3. However, it is the recommendation of PEP8 and the Python community that we always use exactly 4 spaces to indicate one level of indentation. Any halfway decent programming editor can insert those spaces for us when we press the tab key. There are several more recommendations, which we're going to go through here quickly. The code on screen right now demonstrates almost all of the PEP8 formatting recommendations, and I'll leave it on screen while I talk us through them. PEP8 recommends that a single line of code should not exceed the width of 79 characters. While this is consistent with displaying the code on a standard text mode interface of 30 years ago, the primary reason for this rule in the modern world of widescreens and resizable windows is that it helps with reading. Even in contexts that have nothing to do with programming, layout designers prefer to limit line width. Import statements should be placed at the top of the file, with standard library imports first, then third-party imports, then imports from other modules within the same project. There should be a blank line between each group of imports. Classes and functions at the top level should have 2 blank lines separating them. Methods within a class should have 1 blank line separating them. Within a function, or method, blank lines should be used to indicate separation of conceptual groupings of code. Don't insert extra spaces before or after parentheses, brackets, or braces. And don't insert spaces before commas or colons. Always put a single space on either side of binary operators, and don't put more than 1 statement on the same line. Comments should be written in a human language, using that language's correct grammar. Preferably, that language would be English if you're going to allow your code out into the wild, because that language is common to the majority of Python programmers. Comments should also precede the section of code they describe and be indented to the same level. Every public module, class, function, or method should have a properly formatted docstring. We'll look at what properly formatted means for docstrings in video 4 of this section. Let's move on to talk about picking names for variables, functions, and methods. Let's move on to talk about picking names for variables, functions, methods, classes, modules, packages, and so on. The overriding rule of Python naming conventions is that the naming style for an object should make it plain how the object is used, not what the object is. That means, for example, that a factory function, which produces new objects, should be named as if it were a class, because the usage case is the same as if it were a class. Packages and modules should have reasonably short names consisting entirely of lowercase letters and, in the case of modules, underscores. Classes should be named with a capitalized first letter and capitals at the start of every new word within the name. This is sometimes called camel case. Exceptions should be classes, and so they should also follow the naming convention for classes, but the last word of their name should be the word error. Functions, methods, instance variables, and global variables should all be lowercase, with underscores separating words. If they are meant to be internal, rather than part of the public interface, their names should begin with a single underscore. The first parameter of an instance method should always be named self. Constants should be written in all capital letters with underscores separating the words. And that's it for PEP8 and the formatting rules that most Python programmers expect other people's code to follow.
So, PEP8 is online at python.org/dev/pep/pep-0008. The legacy in that URL has been supplanted since I created this slide. The number 1 PEP8 guideline is don't follow it slavishly. Use it when it makes your code easier to read. Don't use tab characters for indentation, ever. Just use 4 spaces. The PEP8 guidelines on the use of blank lines and spaces make a big difference in code readability. And the conventions about the use of capital letters convey a lot of information and should not be disregarded lightly. In the next video, using virtual environments to create a stable and isolated work area. 3.2, using version control. So we're going to look at using version control as an undo history, splitting off branches to develop subprojects, merging code from different branches or repositories, and we're going to use Git for all of these examples because it is presently the most widely used version control system.
Version control is one of the fundamental tools for most programmers. It helps us with almost every aspect of a project in one way or another. There are many version control systems, and each of them is a topic in itself. So we're going to narrow our focus and talk about how to use a few particularly useful things in the Git version control system. The first thing we need to do to use Git, after installing it of course, is to set up a folder as a Git repository. That only takes a couple of commands on the command line after we move to the folder where we want the repository. Git init and git add. Once we've initialized the repository, we add any files that we've already created to it with git add, and then we create our first save point in the code with git commit-a. In the future, if we want to add new files to the project, we should also use git add to tell Git to start tracking them. At any time we want Git to remember the current state of our project, we run git commit-a again. The nice thing about having old project states saved away is that we can go back. If we want to revert a file back to a previous state, undoing everything that we've done since that particular commit, we just use the git log command to find the identifier for that commit, and then use git checkout to undo our changes. If we later change our mind, we can redo the changes in the same way. The ability to undo on the project level is great, but even more useful is to make provisional changes to our code and then decide once the changes are done whether or not we really want them in our main branch. And that's what branches are for. We make a new branch using the git branch-t command and then switch to in and out of that branch using git checkout. Once we're in the branch, any code changes we make are associated with the branch, and when we leave the branch, they go away. Then, when we re-enter the branch, they come back. That means we can do bug fixes in our main branch while we work on our new features in their own development branches. When we're finally happy with a feature, we can merge it into the main branch. To merge code from a different branch, all we have to do is use the git merge command from the branch we're merging to, and give it the name of the branch we're merging from. If the two branches can be combined automatically, Git will do it for us. That's usually all there is to it, but sometimes there will be overlapping changes in both branches, and when that happens, Git knows it's not smart enough to handle the merge on its own. When we run git merge, notify us that there are conflicts. Then we can use git merge tool to start up an interface that lets us use our greater intelligence to resolve the conflict. Once done, we use git commit to finalize the changes. Git can do something very similar to combine code from other repositories into our own. The command for that is git pull rather than git merge. Instead of a branch name, we provide a URL or the path name to a different repository. But otherwise, it's the same. This is an incredibly useful feature because it allows us to easily collaborate with other coders, both locally and around the world.
If our code is in version control, we can roll it back to any point in the history of our project. Branches give us a place to develop and debug specific features without messing up our main code. And merging gives us a way to integrate code from multiple sources, whether they be branches or other repositories.
In the next video,
using virtual environments to create a stable and isolated work area. 3.3. Using virtual environments to create a stable and isolated work area. The venv tool sets up a work area with a private package library and a specific Python version. We're going to see how to use venv and pip to set up a work area, and we're going to see how to activate and work in the work area once it's been set up.
when we're working on a project, we'd usually like the parts of the project that aren't our own code to stay the same. We might have a good reason to install a new version of Python or an updated library on our system, but we don't really want those changes to happen within our development environment. Even more so, we can easily find ourselves targeting entirely different and incompatible system configurations with different projects. We need a way to set aside an area for each project that is separate and can be configured for the specific needs of that project. That's what we call a virtual environment, and the venv tool that's built into Python version 3.3 and later creates them for us. Each virtual environment created by venv knows which version of Python it should be using and has its own package library, which means that as far as Python code is concerned, it's basically disconnected from the rest of the system. We can install, uninstall, and update packages on the system, and code inside the virtual environment won't even notice. We can install new versions of Python, and the code inside the virtual environment won't even notice. About the only thing we can't safely do at the system level is uninstalling the version of Python that the virtual environment is based on. It's easy to create a virtual environment for a new project. We just open the command line and go to the folder where we want the project folder to reside. Then we use the version of Python that we want the virtual environment to use to run the venv tool and tell it the name that we want to give to the project folder. The venv tool will create the project folder and populate it with the files needed to support the virtual environment. When we actually want to work inside the virtual environment, we should activate it. To do that, we open the command line and go to the folder containing the virtual environment, then execute the activation command. The specific activation command depends on the operating system we're using. On most Unix-style systems, including Macintosh, we use the command source bin/activate. On Windows, we run the scripts/activate.bat file. When we're operating inside an activated virtual environment, pip automatically knows it should manage packages for that environment. Initially, the virtual environment contains only the standard Python library and a couple of utilities, including pip. But we can use pip to install the third-party packages that we're going to use on the project. They will automatically go into the virtual environments library. Now that everything's set up, we can begin to work. We shouldn't delete any of the files or folders that venv created, but other than that, we're free to create files and folders as needed for our project.
A virtual environment keeps our project's underpinnings stable. The Python version and installed libraries remain the same for the life of the project. A virtual environment is created from the command line with python-m venv. Inside of a virtual environment, pip installs to the private package library automatically, so there's no need for --user or any similar switch.
Now that we've seen all that, we're going to take a closer look at docstrings. In the next video, we'll learn how to structure our docstrings for maximum utility, how to add rich text formatting to them, and how to export them into hyperlinked HTML documentation for viewing in a web browser.
3.4. PEP 257 and Sphinx. We're going to see how to format our docstrings to get the most use from them, and we're going to look at the restructured text markup format. Then see how to feed those two things into the Sphinx documentation compiler, and to create HTML pages for our documentation of our project.
PEP 257 documents the expectations of Python programmers and tools with respect to docstrings. The basic rules are quite simple. Use triple quotes to delimit the docstring. The closing triple quotes should be on a line of their own, if the docstring is longer than one line. The first line should present a short description of the thing being documented, such as return and distance between points A and B. After the first line, we can either end the docstring, or insert a blank line followed by more in-depth documentation, containing descriptions of parameters, attributes, usage semantic, examples, and so on. The reason for this layout is that many tools show the first line as a pop-up, tooltip, or otherwise presented as a quick reference. The text after the blank line is presented when a detailed documentation is requested. The docstring processing tools are smart about indentation, so it's safe and encouraged to indent our docstrings so that they match up with the rest of the code block they're describing. Those basic rules are all that's required to make the docstrings interact well with Python's PyDoc and help tools, IDEs, and so on. But they don't give us any way of creating well-formatted standalone documentation. That's where Sphinx comes into play. Sphinx is a tool that can process Python source code in standalone documentation files and generate nicely formatted documentation in a number of formats, notably including HTML. Sphinx, like other Python documentation tools, recognizes a markup language called restructured text, which is intentionally readable and informative even when its markup is presented as plain text rather than being interpreted. Restructured text documents are still readable in a simple text editor, but when we feed them through a tool like Sphinx, they make the end result much richer. Restructured text syntax is based on the conventions that developed on the internet before actual rich text was widely available in email and real-time chat. So, for example, words are emphasized by putting an asterisk at each end, and emphasized further by making that into 2 asterisks. Paragraphs are marked by placing a blank line between them. There's syntax for lists, headings, and so on, plainly readable in text mode. The syntax is nicely described in the Python Developer's Guide on the Python website, but we're going to concentrate on a few bits of markup that do a lot to enhance the documentation of our modules and packages. We've actually already mentioned one of those bits of markup. When our doc strings make reference to a local variable such as a function parameter, that reference should be enclosed in asterisks to emphasize it and make it distinct from the normal text of the documentation. The names of modules, classes, functions, methods, attributes, exceptions, global variables, and constants should all be marked properly so that Sphinx can cross-reference them and create links to their documentation. All of these object types share a similar syntax, which is that we put a type-identifying keyword between colons, immediately followed by the name of the object in back quotes, as you can see in this example. That's enough restructured text syntax to make a big difference in the quality of our documentation, so we're going to leave it there and move on to talking about how to actually use the Sphinx tool. If it's not already installed, we can install it using pip. Sphinx can do a lot, so it's worth looking through the tutorial on this sphinx-doc.org. It's quite nice. For our own purposes, though, all we're interested in is turning doc strings into HTML. So we'll work through that process here. The first step is to start a command line and go to the directory where our project lives. Once there, we run Sphinx Quick Start to set things up. The first thing Sphinx Quick Start asks is what the root path for the documentation should be. I find that it works well to use a folder called docs for this, so I suggest typing docs here. Sphinx Quick Start will ask several more questions, which we can answer as we like, and then eventually it will ask if we want to enable the AutoDoc plugin. We do. The rest of the questions are not so important for our purposes. Once Sphinx Quick Start is completed, we'll want to run Sphinx API docs to automatically generate Sphinx source files describing our package. Our doc strings are extracted and incorporated into these source files. Next, we need to modify the conf.py file in the docs directory so that the Sphinx tools will be able to find our package while they generate the documentation. That's easily done just by modifying sys.path. Finally, we want to generate the HTML, which we can construct by make HTML from the command line. Sphinx will translate its source files, including the ones automatically generated by Sphinx API doc, into HTML and store the result in the build directory that we specified when we were going through the Sphinx Quick Starts questions. If we edit our source code and want to update the HTML documentation, we can usually do it simply by running make HTML again. If we've made major changes to the package structure, we'll need to run Sphinx API doc again as well. So, Sphinx can be used as a documentation compiler, which turns our doc string source code into HTML compiled code. That's it for Sphinx and PEP 257.
So doc strings are most useful when they have the right shape, with a short introductory piece on the top line, a blank line, and then more in-depth documentation. Using restructured text allows us to use rich text in our doc strings without excluding people who are using it as a plain text source. And Sphinx can compile our doc strings and separate documentation files into an integrated and cross-referenced HTML document.
In the next video, we're going to look at one more cool advantage that we can get from doc strings by actually executing the examples we included in our documentation and making sure they agree with what the code actually does.
3.5 Doc Test. We're going to look at how to make sure our documentation is accurate by running the examples as code. Similarly, how to make our code correct by checking it against the documentation.
It's common to include examples of use in our doc strings, but if we're not careful, those examples can get left behind when the code changes, and wrong documentation is worse than no documentation. Fortunately, we have a tool that can check whether the documentation agrees with the code by running the examples from our documentation and seeing what happens. That tool is called doctest. To enable doctest to recognize our examples as things it can test, all we have to do is include the Python interactive shell prompt into our example. In the simplest and most common case, that just means putting a triple greater than symbol in front of each statement. For multi-line statements, we prefix each continuation line with a triple dot symbol. After each statement, we should write down the expected result of the statement, written in the same way the interactive shell would write it. In other words, if we copy and paste directly from the interactive shell, we've created an example that doctest can recognize. So, writing doctest is pretty straightforward. There's a decent chance of writing a doctest into our doc strings even if we didn't know the doctest tool existed. As an added bonus, Sphinx recognizes doctests and formats them appropriately too. So if we're going to include code examples in our doc strings, this is the way to write them. It's easy to have doctest run all of the examples in the doc strings of a source file and report back whether they worked. We just run the doctest utility from the command line and tell it which file we're interested in. The -v option makes it print out extra information, which isn't necessary but is often helpful. There are other ways of running doc tests, including a Sphinx plugin that Sphinx Quick Start asks us whether we want. It's also possible to integrate doc tests into a test suite in Python's standard unit test library, or to use an integrated test runner called nose to find and execute them. Running doctest direct will do for our purposes here, though. Now, what happens if a doc test fails, but after looking at it, we see that the documentation and example are actually correct? Well, that means that our code is incorrect. Believe it or not, this is a very good thing. I don't mean that having an error is a good thing, but that error was there whether we found it or not. Finding it, and having a test on hand that will let us check whether we've succeeded in fixing it, that's good. So doctest ties our code and documentation together so that they stay synchronized and serve to double-check each other. That's a very useful doc string trick.
So running the examples in our documentation through doctest highlights when the documentation disagrees with the code. If the documentation is correct, failing example means our code is flawed. Similarly, if the code is correct, then the documentation needs to be updated. The doctest tool makes it easy to check all of our examples.
That's it for the basic best practices section. In the next section, we'll see about putting together a command line utility program.
Section 4. Making a command line utility. 4.1. Making a package executable via Python-m. So we're going to look at what Python's -m command line option does, where the execution starts when we use Python-m to run a package, not a module, how to keep the program from running when we don't want it to, and getting started on a project that we'll work through in the remainder of this section.
In previous videos, we've run command line tools like doctest and venv by typing in Python-m followed by the name of the tool we wanted to run. What were we actually asking Python to do when we did that? The -m command line switch for Python tells it to run a module. It uses the same mechanism to find the module that it would if we'd used the import statement with the module's name, and then it executes it. But venv isn't a module, it's a package. So what's happening when we do Python-m venv? We gave Python a package name, but we didn't give it a module name inside the package that it should run. When that happens, Python looks for a module named __main__ in the package, and runs that. So Python-m venv means the same thing as Python-m venv.__main__. Any module that's meant to contain a program's entry point has a problem, because simply importing the module will run the code too. That can be annoying or troublesome at the best of times, but it becomes unacceptable when we're using tools like Sphinx or doctest that need to import modules in order to do their jobs, but which really shouldn't actually run the module code as a program. Fortunately, there's an easy fix because the Python interpreter itself knows which module it was told to start running and marks it as such. All modules are automatically given a variable named __name__, which contains the module's name except in the case of the program entry point. The program entry point is always given the name __main__, even if its file name is something entirely different. So we can check whether our code was the program entry point by checking if name equals main. If it does, we should run the program. If it doesn't, we were imported normally and should act as just a simple module. This even distinguishes between importing a module's main module, and running it. This even distinguishes between importing a module as main module and running it, because when we import it, the name variable contains package name dot underscore underscore main underscore underscore, not just underscore underscore main underscore underscore. In the videos in this section, we're going to work through the process of building a complete utility program called Pipeline. Pipeline will be a text mode program that can be configured to run a sequence of other programs and feed data from one programming to the next. In each video, we'll apply what we've talked about in developing Pipeline further. So far, all we've talked about in this section is how to make a program able to be run from Python-M. But we've seen in previous sections how to create a virtual environment to work in, how to create a package, and how to lay out the code in the package's modules for readability. So let's put those lessons to use. Create a folder within the virtual environment to be the package and call it Pipeline. Inside the package folder, place an init.py file, which can be empty, and a main.py file. For now, the contents of the main file can be very simple. Just a docstring for the module, a function that should be called if the module is the program entry point, and the if statement that decides whether or not to call the launch function. The launch function doesn't have a docstring, which is allowed because it's marked as non-public by having an underscore as the first letter of its name. The launch function also doesn't do anything interesting yet. It just uses the print function to tell us that it was successfully executed. Let's run it so we can see for ourselves. Open a command line, go to the virtual environment where we created the package, and activate the virtual environment. Then type python-m pipeline. That's it for how to make a package run as a program.
The -m command line option imports a package or module and runs it. When we ask to run a package, execution starts in the double-underbarred main module, if it exists. If it does not exist, an error will be raised. We can use the if double-underbarred name equals double-underbar main construct to protect our code from running just because it's been imported, and run only when it's actually executed, intentionally.
In the next video, we'll move on to how to handle the command line arguments.
4.2. Handling command line arguments with argparse. We're going to see how to create an argument parser object and how to tell it what the command line switches and arguments it should look for are. And then we're going to perform the next step of our project.
Most command line programs, and a surprising number of graphical user interface programs as well, can be given extra information on the command line after the command that invokes the program. These extra bits of information are referred to as arguments or switches, and they are delivered to Python programs as a list of strings. It turns out that there's quite a lot of code involved in turning an argument list of strings into useful information, especially when we want to make the program as convenient for our users as possible. Fortunately, a lot of that code can be the same from program to program, and the Python standard library's argparse module takes care of much of the effort for us. The primary component of the argparse module is the argument parser class. In the minimal case, it only takes 3 lines of code to use argparse. We need to import it, create an argument parser instance, and call that instance's parseargs function. As usual with minimal cases, it's not very useful. The only arguments that the program would respond to are -h or --help, either of which would print out an automatically generated how to use this program message and then exit the program. The first thing we can do to make the argument parser more useful is provide a value for the description parameter of its constructor. The argument parser's automatically generated help message will explain all of the arguments that the program expects, but it doesn't say anything about what the program is actually supposed to do, unless we provide the description ourselves. In this case, we've just put in hello world. In real cases, we would generally want to put more useful information than that. The next way we can improve the argument parser's behavior is by telling it the name of the program. If we don't provide a name, it will do its best to make a reasonable guess, but we're better off telling it ourselves. I consider the python-m command to be the canonical name for my own programs, so that's what we'll use in our examples. We set up the name by passing it as a string to the argument parser constructor's prog parameter. These changes make the program's output prettier and more useful, but they don't actually give the program any new capabilities. We need to start adding argument specifications to the parser so that it can check for them. We need to start adding argument specifications to the parser so that it can check for them in the argument list. We do that by calling the argument parser instance's addArgument method. Argparse recognizes 2 kinds of arguments, optional arguments and positional arguments. As the name implies, optional arguments are not required, but if the user chooses to include them on the command line, they have meaning. Positional arguments, on the other hand, are required by default, although we can modify that behavior. Optional arguments have names that start with a dash character, and can have more than one alternate name for the same argument. The names are passed as parameters to the addArgument method, as in this example, where -p and -print are alternate names for the same optional argument. There are a lot of ways of configuring an argument when we add it to the parser, which are detailed in the argparse documentation in the library reference on docs.python.org. For options like our print example, though, the important configuration items are the action and the default. The action tells argparse what to do when it finds the argument on the command line, and the default tells it what to do when it doesn't find the argument on the command line. The action parameter can be either a string containing the name of a well-known action, which are predefined and documented on docs.python.org, like store true, or it can be a subclass of the argparse.action class if you want to customize it for yourself. The default can be any arbitrary value, which will be stored as the value of the argument if it's missing when we actually ask the parser to parse the argument values. The other kind of argument has to have just one name, and it can't start with the dash character. By default, these arguments collect one word that isn't part of an optional argument from the command line, in the order that they were added to the parser. If we configure the argument using the nargs option, we can change the number of words that the argument collects. If we set nargs to a number, If we set nargs to a number, that many words will be collected for the argument. We can also set nargs to star to mean any number of words, or plus to mean at least one word. There are a few other values we could set nargs to, but we won't talk about them here. Let's look back at our pipeline program. I think we want it to understand two arguments. An optional argument that tells it to keep going even if one of the programs returns an error code, and a file name where it should load and store the pipeline configuration. After the call to parse args, we have an object named args that contains a keep_going attribute set to either true or false, and a file name attribute containing a string. Notice that the attribute of the arguments object is keep_going, not keep-going. Python doesn't allow dash characters inside of attribute names, and argparse is smart enough to fix that for us automatically. If we wanted to set the name of the argument object attribute manually, we could have passed the name we wanted to the addArgument method as its dest parameter. That's D-E-S-T. Now that we've worked out how to read the information that's given to us when the program starts,
So command line parsers are created with argparse.argumentParser. The parseArgs method reads the command line and generates an object containing the arguments. And the parsed arguments do not have to be strings. They can be numbers, lists, and so on.
in the next video we're going to look at how to interact with the user while the program is running.
4.3 Text Mode Interactivity. We're going to look at basic input and output using print, pprint, input, and getPass. Or we're going to see about using the CMD command framework to create a more advanced text mode interface. And then we're going to execute the next step of our project.
The fundamentals of interactivity are simple. We need to be able to tell the user things, and we need the user to be able to tell us things. In service of those two goals, Python provides the built-in functions print and input. Print takes any number of Python objects as parameters and prints them on the screen. Input takes a string prompt as its parameter, prints it out, and then reads text until the user hits enter, and returns what the user typed as a string. That's about as simple as interactivity can get. The print and input functions can do a lot, but there are a couple of corner cases where they don't work so well. One of those is when we want the user to type in a password. If we used input to read the password, it would be displayed on the screen for anybody else to read. The getPass module contains a function called getPass, which works just like input, except that it doesn't show the text the user types. The other corner case I want to mention is that although print can print out any Python object, it doesn't do a good job of presenting complex data structures. The pprint function, from the module of the same name, makes complex data structures much more readable. If we want to display a list of dictionaries, pprint will do a better job of it than print would. Between those four functions, there's a wide range of user interfaces we could make, but they're pretty basic tools. We'd be reinventing a lot of wheels and wasting time. Fortunately, thanks to Python's batteries-included philosophy, we don't have to do that. Instead, we'll use the Steidner library's CMD module to quickly build our user interface. All we have to do is inherit from the command class, that's cmd.cmd, and define the methods which implement commands the users can type. We set the prompt attribute to a string that will be used to prompt the user for a command, and then we create an instance of our command class and call it cmd loop command loop method. Presto, instant interface. In the example we just saw, the command class takes care of displaying prompts, reading in commands, and invoking the correct methods. But that's all it does. We still needed print if we wanted to display data from inside the command handler method. The command class isn't exclusive. It does a lot of work for us, but we can still use print and input directly if we need to. That's very nearly everything there is to say about text mode interactivity in Python, at least if we want our programs to be portable across platforms. There is another standard library module called curses, which enables much more sophisticated text mode operations. But the curses module is not portable to Windows, and so we're not going to go into it in details here. Instead, let's look at defining the user interface for our pipeline program. It seems like we'd want to be able to add programs to the pipeline and manipulate the data passing between the programs in various ways. We'll also want to be able to save the pipeline when we're happy with it and be able to actually run it. Finally, we'll want to be able to quit the program. A help command would also be helpful, but lucky us, the command class will provide that automatically by using the doc strings for the command handler functions. We're just going to stub in the command handlers here because we're focusing on the interface implementation for now. So there we have a pretty decent user interface, and with very little work on our part. That's it for the text mode interaction. The built-in print and input functions provide basic input and output. The pprint module gives us a nice formatting for displaying Python objects, while the getPass module provides hidden password input. The CMD module provides a more advanced framework for quickly creating text mode interactive programs. In the next video, we'll look at how to actually run other programs from inside our code. 4.4, executing other programs. We're going to look at how to run a program and wait for it to finish, or how to run a program in the background while our code is still running. We're going to see how to interact with programs running in the background, and then we're going to write the next step of our project. Making other programs run used to be something of a mess. There were different mechanisms that worked on different platforms, there were mechanisms that were convenient, and then there were different mechanisms that were secure. Fortunately, that all changed in Python 2 version 2.4, with the introduction of the subprocess module, which abstracts away the differences between platforms and makes the more secure paradigms easy to use. There are 5 objects in the subprocess module that are of particular interest. 3 of them are the call, check call, and check output functions, which are 3 variants of the same basic idea. They run a program, wait for it to terminate, and then tell us something about what the program did. The call function returns the program's exit code. The check call function raises an exception if the program's exit code was non-zero, which by convention means that it exited with an error. The check output function returns whatever text the program printed, and raises an exception if the program exited with a non-zero exit code. The raised exception has an attribute called output that contains the text output of the program, so even if the program exited with an error code, we can still get the output if we wanted. The 3 call functions are invoked largely the same way. Each of them is passed a list containing the program name and its arguments. The check output function has a noteworthy keyword-only parameter called universal newlines, which defaults to false. If we set universal newlines to true, the text output of the program is decoded into Unicode characters using the system's default text codec, and newline characters are normalized. If we leave universal newlines at its default value of false, the program output is returned as bytes, and it's up to us to do any decoding and to deal with whatever sequence of characters the current system considers to be a newline marker. If we want to get fancy with our running of other programs, we'll want to use the popen class, the 4th interesting thing in the subprocess module, which allows us a great deal of flexibility and control over the execution of other programs at the cost of a bit more complexity. The popen constructor accepts the same list of program and command line arguments as the call functions do, and a very large number of optional keyword arguments, including universal newlines. We're going to focus on the particular use case of popen that is useful but goes beyond what we can achieve with the call functions. We're going to see how to run a program in the background, while our own code is running in the foreground, and send and receive data between the 2 programs. To manage that, we're going to need the last of our 5 interesting things from the subprocess module, the pipe constant. The pipe constant is used in conjunction with the standard in, standard out, or standard error keyword argument parameters of the popen constructor. These parameters represent the other program's textual input, output, and error reporting, and any of them that we set to pipe are redirected to our program. In this example, we're redirecting the program's input and output to ourselves, which gives us a bidirectional data channel with the other program. Once we have pipes set up, we can send data to the other program by calling the write method on the popen object's standard in attribute, and we can read data by calling the read method or its relatives on the popen object's standard out attribute. Note that these are input and output as from the perspective of the called program, the subprocess, and therefore sort of backwards from the perspective of the program that's running in the foreground. In spite of disabling buffering with the buff size equals 0 parameters in this example, it's usually a good idea to call the flush method on standard in after writing to it, and the flush method on standard out before reading from it. We can keep on sending and receiving data for as long as both programs are running, but if the time comes when we're done interacting and we just want to wait for the other program to terminate, we can call the popen object's wait method to do that. The wait method will return the exit code from the other program, once it's done running. A lot of the complexity of working with piped standard in and standard out is wrapped up in the popen class's communicate method, which accepts input as a parameter and returns output. Communicate is simple but somewhat limited because it can only be called once for each popen object, and doesn't return until the other program finishes. That isn't any good for two programs that need to talk back and forth to each other, but it should be just perfect for our pipeline program, where each program receives the output of the previous program as its input. We're going to create a bunch of classes to represent the different kinds of steps that can take place inside a pipeline stream, and integrate classes into the interface as well. Once we've done that, the program is functional, though there's still plenty of room for improvement. We've got our example program working, so the call, and check output functions of the subprocess module give us an easy way to run other programs. If we need more control over the other program, we can create a popen instance to interact with it. The popen methods pull, wait, communicate, and terminate are particularly useful. So we're going to move on to the next topic of this section, setting up a shell script or batch file to launch the program. 4.5, using shell scripts or batch files to launch programs. We're going to see how to use a shell script to run our program under Unix and Mac OS X, or a batch file to run it under Windows, and we're going to set up the last step of our project. We can run our program using python-m as long as it's installed in the Python path or we've activated the virtual environment containing it. But once the program is solid, we really just want to be able to type its name or double-click on it and have it run. One convenient way to do that is to use the shell script or batch file. On Unix-style operating systems, including Mac OS, a shell script is a text file that starts with the #bang/bin/sh and has been marked as executable. On Windows, a batch file is a file whose name ends in .bat. Both shell scripts and batch files are text files containing a sequence of command line commands, one on each line. When we type the name of the script or batch file, the commands are executed one after another, as if we typed them all into the command line. Similarly, if we trigger the script or batch file through a graphical user interface, the commands are still executed as if we typed them into the command line one by one. For our purposes here, that means we can put whatever sequence of commands necessary to launch our program into a shell script or batch file, and after that we can treat that script as if it were the program itself. That's all there is to the simple case. Shell scripts are capable of representing a lot more complexity, but Python is a better tool for that, so the simple case is all we really need. That's it for our section on creating a command line utility. We've actually made a somewhat useful tool, and we can do it again whenever the need arises. So a shell script or batch file gives us a simple way to launch our program. This gives us a way to run the program that works just as well from the graphical interface or the command line. In the next section, we're going to look at how to do parallel processing in Python so we can take advantage of multi-core CPUs and multiple CPU computers to maximize our data processing rates. Section 5, Parallel Processing. 5.1, Using concurrent.futures. We're going to look at when it's beneficial to split a program into multiple simultaneous processes. Then we're going to see how process pool executor and future objects allow us to farm out tasks to worker processes. Some programs are what we call CPU bound, which means that the primary factor which determines how long the program takes to complete is how fast the computer can run through its instructions. Interestingly, most programs that we use on a daily basis are not CPU bound. However, for those that are, we can speed them up by breaking them into separate processes that run on separate CPUs or separate CPU cores. This has the net effect of increasing the number of program instructions executed per second, which means the CPU-bound programs run faster. In some programming languages, we can see that same benefit by running multiple threads for a single program. However, as I mentioned before, most programs are not CPU-bound, so the creators of Python have chosen to optimize Python's threading system for the common case, which has the side effect of making Python threads not very useful for improving the speed of CPU-bound programs. Besides, it's easier for the operating system to optimize the execution of multiple processes than multiple threads within a process. So even if threading were a viable option, multiple processes would be a better choice for a CPU-bound program. We've already seen one very low-level approach to launching a process and communicating with it, in our discussion of the subprocess module. However, for cases where the reason we want to do that is because we want our program to be broken up into a bunch of cooperative processes that work together, Python provides us with a couple of higher-level toolkits that make things easier. The more abstract of Python's parallel processing toolkits is called concurrent.futures. The concurrent.futures module is designed for programs that can be structured with one controlling process and several worker processes, where the controlling process hands out jobs to worker processes and then collects and collates the results. That's a fairly generic model, especially for CPU-bound programs. So concurrent futures is widely applicable as it is simple to use. And it is simple. The basic usage is just to import it, create a process pool executor object, and then call that object's map or submit methods to send work to the worker processes. When we're completely done with the process pool executor and we know we'll never need it again, we call its shutdown method or allow the with statement to do it for us. The process pool executor will take care of all the twitchy details of creating and communicating with worker processes. When we call the process pool executor's map or submit methods, we're asking it to call a function with the given parameters, but we want that function call to happen inside of a worker process, not inside the main controlling process. That has some implications that might not be obvious. First of all, it means that the function and its parameters need to be pickleable, which is another way of saying that Python needs to know how to turn that into a byte string that it can send to the worker process. For functions, that basically means any function is okay unless it was defined inside the body of another function. For parameters, it means that most objects will work, but generators and a few other kinds of special objects cannot be passed. It's important to be aware that both the function and the parameters passed to it can easily bring along information we didn't intend to send and when they get pickled for communication to the worker process. If any of the objects we send to the process pool executor references other objects, those objects get pickled up and sent too. It's entirely possible to end up sending most of the state of our program. That's particularly worth noting when the function we're asking to run is a method of an object. If the function is a method of an object, the whole object will get pickled and sent to the worker process, which means that the function call will be happening with a copy of the original object as its self parameter, not the original object itself. Second, the return value of the function is pickled and returned to the controlling process. All of the warnings about passing parameters to the called function apply to the return value too. So for example, the function can't return a generator object, and if the return value contains references to a bunch of objects, copies of them will end up being sent to the controlling process. Third and finally, the concurrent.futures code that's running in the worker process needs to be able to import the modules that our original code was loaded from. That means we may need to use the if name equals main trick to keep the worker processes from getting stuck running complete copies of our original program when all they wanted to do was import the module to find the function they were asked to run. We've already seen the map method of the process pool executor in our example, but let's look a little closer. The map method takes a function as its first parameter. We can also pass it one or more iterables, which will be used to figure out the parameters for each call to the function. So, if we ask the pool to map the foo function to the lists 1, 2, 3, and 4, 5, 6, the result is that foo will be called with 1 and 4 as its parameters, called again with 2 and 5 as its parameters, and called a third time with 3 and 6 as its parameters. There's no guarantee about which order these three calls will happen in, though. After all, they're likely to each run in different processes, and the relationship between the process scheduling and wall clock time is partly dependent on unpredictable factors. The map method hides that fact by waiting for all the calls to finish and produce their results, and then returning an iterator that over those results in the proper order. Sometimes the map method is too simple. What if we want to handle the results as each worker process produces them instead of waiting for all the workers to get done? What if we decide not to run the function after all? What if we want to run different functions in worker processes at the same time? For that matter, what if we want to pass keyword arguments to the function? We can do all that and more using the submit method. Each call to submit translates to a single call to the function that we pass as its first parameter. The rest of the parameters and keyword arguments we pass to submit are passed into the function after being sent to a worker process. So, for each time we call submit, one worker process calls one function with one set of parameters. Submit does not wait for the worker process to finish running before returning. In fact, it doesn't even wait for the worker process to start running the function. And so submit does not return the result of the called function. Instead, it returns a future object. A future object is in some sense an IOU for the result of the function. If we have a future object, we can use it to check whether the worker process has finished running the function, to get the result returned by the function, or even to set up a callback that will be called when the function finally does finish running. We can even use the future object to remove the function call from the queue of jobs that should be shared out to the workers. The done and result methods of a future object are the ones that we'll use the most often. The done method returns true if the job is done and false if it's not. A job is done if it was cancelled, if it raised an exception, or if the job function has returned. The result method returns the return value of the job function if the job completed successfully. If the job function raised an exception instead, the worker process will catch the exception and hand it back to the controlling process as the result of the job. In that case, calling the result method will re-raise the exception so that it can be handled properly. as is foo error in the example on screen at the moment. If we call the result method before the job function is done, the result method will wait for the job to complete before it returns. That can be very useful, but sometimes we don't want to wait indefinitely. If the job isn't done quickly, we want to go on and do something else for a while. In that case, all we have to do is pass the number of seconds we're willing to wait to the timeout parameter of the result method. If the timeout expires without the result being produced, a timeout error will be raised. There are a pair of functions in the concurrent futures module that let us wait on several futures at once. They're called wait and asCompleted. The wait function waits until all the futures are ready to deliver their results, or until the timeout expires. Then it returns a set of features that are done and a set of features that aren't. In contrast, the asCompleted function returns an iterator that produces features one by one as they become ready to produce their results. This is, in many cases, the easiest way to deal with multiple features simultaneously. In rare cases, the done and result methods of future and the wait and asCompleted functions of the concurrent futures module aren't sufficient to let a program process features at the proper time. For those occasions, it's possible to have the feature call a function when the result becomes available. We can do that by passing the function into the feature's addDone callback method. The feature will remember that function, and when the job function is done, the callback function will be called with the future object as its only parameter. The code in the callback function can then call the future's result method to get the return value or exception that the job produced. Take note that the calling function will always be called in the controlling process, but it might not be called in the same thread as the main part of the program. When we use addDone callback, we need to be careful of thread synchronization issues, which is a big reason to prefer wait or asCompleted when possible. Future objects also have a cancel method, which tries to tell the system that we don't want the call to happen after all. This is not guaranteed to work, because if a worker process has already begun the job, the cancel method will not be effective. If the job connected to a future can't be canceled, the cancel method returns false. If the cancellation succeeded, the cancel method returns true. The concurrent futures module is perfectly suited to farming out computational tasks to multiple processes to take advantage of the CPU power of multi-core and multiprocessor computers. The map, submit, wait, and asCompleted functions are usually all you need for that kind of task.
When the main limitation on program speed is how quickly the CPU can run code, splitting that program into multiple processes can help it run faster, at least on multiprocessor systems. A process pool executor handles all the bookkeeping that's required to create and manage worker processes. When a task is given to a process pool executor to be shared out to a worker process, a future is returned. A future allows us to cancel the task, to check whether it has been completed, or to wait for it to finish and retrieve the result.
If the program we need doesn't fit into the send out jobs and collect the results model, we're probably better off working at a somewhat lower level using the multiprocessing module, which is the topic of the next video.
5.2 Using multiprocessing. What if our program is CPU bound but doesn't fit the concurrent.futures model? We're going to look at creating parallel processes using the multiprocessing package, transferring data between those processes, and keeping the processes synchronized.
Imagine for a moment that we're writing a program that is CPU bound, and we can break the program's duties up into several pieces that could be run simultaneously on different cores. But the pieces are only partly independent of each other. From time to time, they need to pass information between themselves, not just back to the controlling process. We can't do that with concurrent futures because it just doesn't fit into the model concurrent futures uses to describe parallel processing. Or, what if we need to be able to cancel a job after a worker process has started running it? Again, that doesn't fit the model concurrent futures uses. The concurrent futures model is powerful, but it's not too hard to imagine scenarios it can't handle. When we need to build our own model of how parallel processing should work, we can use the multiprocessing module as the foundation. The multiprocessing module contains a class called process that represents the ability to run code in a separate process. Probably the simplest way to use the process class is to subclass it and override the run method, which is the entry point for code in the other process. In this example, we've created a specific kind of process that calculates some square numbers. Then we create an instance and start it running. When we called start, the multiprocessing module did the necessary work to make sure that the run method was executed in a new process. By the way, all the warnings we discussed in the concurrent futures video about pickling and importing modules applies to multiprocessing as well. When it comes to moving data between processes and importing code, they work in the same way. So far, we haven't seen anything that we couldn't do better with concurrent futures. Let's have a quick overview of each, and then we'll look at them in detail. Queues are communication channels that are appropriate for one-to-any, any-to-one, or any-to-any communications between cooperating processes. depending on how they're used. That makes them ideal for posting tasks to worker processes when we don't care which worker ends up with doing the task, and for collecting the results of multiple worker processes. Any process can put a pickable object into a queue, and any process can remove an object from the queue. Queues are first-in, first-out data structures, which means that objects are removed from the queue in the same order that they're added. There is a subclass of queue called joinable queue, which adds a method which allows the process to wait until the queue has been emptied by other processes. Pipes are one-to-one communication channels. When we call pipe, we get back a pair of objects that serve as one end of a communication stream. If we give one end each to a pair of processes, they can send messages and data back and forth through the pipe. It's usually best to have queues and pipes as the only connection between processes, because that usually maximizes the ability of the processes to work in parallel. If it's possible to organize a parallel program that way, it should be. If we find we need to share some variables between several processes, though, we can do it using a manager object. A manager represents a special process with only one task, keeping track of the variables the other processes need. Accessing variables stored in a manager is much slower than accessing a process's local variables, and it can lead to situations where processes trying to access variables at the same time slow each other down. On the other hand, if we actually need shared variables, at least the manager handles them correctly and as efficiently as possible. Okay, let's take a closer look at queue objects. There are three methods that are primarily useful: put, get, and getNoWait. When we call put, an object is placed on the back of the queue. When we call get, an object is removed from the front of the queue and returned, unless the queue is empty. If the queue is empty, the process that called get waits until it is able to remove an object, which will happen after some other process puts an object into the queue. When we call getNoWait, on the other hand, it either removes and returns the object at the front of the queue, or raises a queue.empty exception. Finally, we can pass a timeout parameter to the get method, in which case it will either remove and return an object within that many seconds, or raise queue.empty. We can pass queue objects around between processes by making them part of a process's initial data, or by sending them through pre-existing queues or pipes, or even by storing them in a manager. Queues are designed to be shared between processes. Moving on, let's look at pipes. Each end of a pipe has the same methods. The interesting methods are send, receive, which is spelled RECV, and pull. The send method accepts an object as its parameter and sends it to the other endpoint. The receive method waits for something to be sent from the other endpoint and returns it. The pull method returns true if there is an object waiting to be received, and false if it's not. If we give it a number for the timeout and there is not currently something waiting to be received, the pull function will wait for up to that many seconds for data to arrive and then return. If no data arrives before the timeout expires, the pull method will return false. If we pass none as the pull method's timeout parameter, it will wait until data arrives before returning, no matter how long that takes. Like queue objects, pipe endpoints can be sent to other processes as they're launched, or through other queues, pipes, and so on after the process is running. Let's look at manager in more detail now. Managers can handle many types of data, but we're going to focus on their ability to store dictionaries, lists, and namespaces. Normally, when we send an object to another process, the other process actually gets a copy of that object. If the other process changes the object it receives, we don't see those changes in the original process. A manager lets us create objects that behave more like queues, in that we send the object to the other process, and that process changes the object. We do see the changes in the original process, or in any other process that has access to the object. The manager dict and list methods create special dictionaries or lists that can be shared between processes. The namespace method, which does indeed start with a capital N, creates a more generic shared object, on which we can set attributes to share them between processes. When we have shared data that are being accessed by multiple streams of execution, which is exactly what Manager provides, we have to be careful to keep the data accesses synchronized. To help with that, managers can also create some standard synchronization primitives, such as locks, events, conditions, and semaphores. Lock objects are the simplest of the synchronization tools. They have a pair of methods called acquire and release. After a process calls acquire on a particular lock, any other process that calls acquire on that same lock is forced to wait until the first process calls release. Then the acquire call in one of the waiting processes returns, allowing that process to proceed. In other words, code between an acquire call and a release call can count on being the only code accessing whatever data the lock is protecting. Event objects allow a process to proceed immediately if a flag is true, or wait until the flag becomes true. The flag is sent to false by calling the event's clear method, or true by calling its set method. When we call the wait method, it will return immediately if the flag is true, or pause execution until another process calls set, and then return. Event objects are useful for making a process pause until some specific thing happens. Conditions combine some of the features of lock and event objects. Like a lock, they have acquire and release methods that can be used to protect data from simultaneous access. However, a condition object also has a wait method and a notify method, which can be used to wait until some other process does something, and to wake up a waiting process, respectively. Condition objects are useful for creating data structures that synchronize access to their contents, and wait when they don't have any data to return. The get and put methods of the queue class could be implemented using a condition. Semaphore objects look a lot like lock objects. The difference is that where lock objects always ensure that exactly one process has acquired the lock at a given time, semaphore objects ensure that no more than a fixed number of processes can acquire it at the same time. This is useful for doing things like limiting the number of processes that can access the hard disk or send data across the network simultaneously. So now we know quite a lot about how to help CPU-bound programs take advantage of multi-core and multiprocessor hardware to run faster. We can use the concurrent.futures module if we have a standard high-level data processing task, or if we need to define our own model of concurrency, we can use multiprocessing to do that. The multiprocessing process class can allow us to create our own subprocesses and interact with them. The process class lets us launch our own processes and manage them, while the queue, pipe, and manager classes give us access to data channels between processes. Meanwhile, the lock, event, condition, and semaphore classes let us synchronize the communications between the processes, keep them from tripping each other up. However, most programs aren't CPU-bound. They're I/O-bound, which means they spend most of their time waiting for input from various sources. Parallel processing doesn't help with that situation.
In the next section, we're going to look at coroutines and asynchronous I/O. Mastering Python, Section 6, Coroutines and Asynchronous I/O. 6.1, Understanding why this isn't like parallel processing. In this video, we're going to take a look at the resource usage of parallel programs and the implications for server processes. When we were working with the concurrent.futures module, we saw a way to make two or more streams of code run at the same time. We could create an executor object, and then whenever we wanted to run code in parallel, we could tell the executor to run the code. The executor would give us a future object that we could later use to get the result of the code, and it would then run the code in a separate process while our original code kept on running in our original process. We talked about how this could improve the performance of CPU-bound programs by letting the code be divided up between multiple computer cores, but it seems like a technique that could be convenient for a lot of other circumstances. It's handy to be able to tell the computer, "Go and do this, and let me know when you're done." One place where that ability seems particularly useful is network server programs, where having a separate stream of execution for each connected client makes the logic and structure of the code much easier to grasp, which means that it's easier to write bug-free servers when they're structured that way. There are ways to write a server that use only a single stream of execution, but if we have a way of writing servers that probably introduces fewer bugs, why wouldn't we? The problem is resource overhead. Every process running on a computer uses up memory and CPU time, of course. But in addition to the memory and CPU time it actually needs to run its code, the operating system also needs to expend resources to manage the process. As it happens, the time spent on switching between processes is significant. The memory overhead is enough that it becomes a limiting factor on how many clients a multiprocess server can handle simultaneously, and other internal operating system resources may be even more limiting. For CPU-bound programs, there's a sweet spot that produces optimal results where the program has one process per CPU core. For an I/O-bound program, which most servers are, any process beyond the first is nothing but overhead. As I mentioned, there are ways to write single-process servers that can handle multiple clients at once. With much lower overhead per connected client, using these techniques actually allows a server to handle many more clients at once than a multiprocess server program could. Even when not operating at full capacity, a single-process server leaves more of the computer's resources available for other uses. So, on the one hand, we have a way of writing servers that is logically structured and less prone to bugs, but wastes resources. On the other hand, we have a way of writing servers that is resource efficient, but easy to get wrong. Can we somehow get the best of both worlds? The answer is yes, fortunately. Python's standard async I/O module combines the low-level techniques that allow a single process to service multiple clients with a cooperative coroutine scheduler. The end result is a programming interface that looks and acts a lot like concurrent.futures, but with much lower overhead per stream of code execution. That's great, but what is a cooperative coroutine scheduler? For that matter, what's a coroutine? A coroutine is a computer science concept, a function that can be paused and resumed at certain places within it.
Each time it pauses, it can send data out, and each time it is resumed, it can receive data. Python generator functions are capable of behaving like coroutines by using the yield statement as the pause and resume points, and async IO takes advantage of that. A cooperative coroutine scheduler is a piece of code that picks up the execution each time a coroutine pauses, and decides which coroutine should get to run next. It's called a scheduler because it keeps track of multiple streams of execution and decides which one gets to run at any given time. It's called cooperative because the scheduler can't yank the right to be running away from a coroutine and give it to another one. It has to wait until the running coroutine pauses itself, and then it can select another coroutine to run. In async IO's formulation of coroutines, the pause and resume points are yield from expressions, which are also how we call other coroutines. Each time we want to perform a function call on a coroutine from inside another coroutine, we yield from that coroutine we want to call. As far as the semantics of the code work, that behaves just like calling a function from inside a function. The other coroutine runs until it returns, and we get back the return value. That's how the code behaves, but what it actually does is quite a bit more. The first thing that happens is that the coroutine we're running is paused. The coroutine we want to call is handed off to the scheduler, which places it into a list of coroutines that need to be run. Then the scheduler checks to see whether anything has happened that a coroutine was waiting for, such as new data coming across the network or another coroutine returning, and if so, it adds the waiting coroutines to the list as well. Then the scheduler picks one of the coroutines that needs to run and unpauses it. That means that if a coroutine has a long-running loop that doesn't contain any yield from expressions, not only will it block any other coroutine from running, it will also keep the program from checking for new data coming in across the network and prevent assorted other input and output operations from being serviced. If we have such a loop, and there's just no reason to call any other coroutines inside it, we can place a yield statement into the loop body, which simply gives the scheduler a chance to do its thing. The little bit of extra complexity that comes from needing yield from expressions and the occasional yield statement is the price of a cooperative scheduling. But since the payoff is efficient and logical code for IO-bound programs, it's often worth it. So we've just seen an overview of how async IO allows us to use the logical structure of a parallel program, while retaining the advantages in terms of code execution of a threaded single-process program. This is advantageous for us when we're dealing with IO-bound programs. In the next video, we'll look at using the async IO event loop and coroutine scheduler. 6.2, using the event loop and coroutine scheduler. We're going to take a look at how to create a coroutine, how to manage the scheduling of them so that they act as if they were parallel processes, at least from a logical perspective. And we're going to see a minimal example of running multiple threads of code execution without running multiple processes. It's easy to create a coroutine. All we have to do is use the asyncIO.coroutine decorator on a function and use yield from anytime we want to call other coroutines. As in this example here where we're calling asyncIO.sleep, which is a coroutine, from with our example coroutine using yield from. Once we have a coroutine, though, we can't just call it to start the ball rolling. If we try to call it, it just immediately returns a generator object. That's not much use. Instead, we need to add the coroutine to async IO's scheduler as a new task, and then we need the scheduler to run, arranging for coroutines to execute and handling input and output events. The async IO package automatically creates a default scheduler, also called an event loop. While it's possible to create new event loop objects, or to replace the default one, for our purposes the default will work fine. We can get a reference to it by calling async IO's getEventLoop function. To tell the scheduler that we want it to start a new task running a given coroutine, we call async IO's async function. By default, this will create a task in the default scheduler, but we can override that by passing an explicit event loop to the loop keyword-only parameter of the async function. Notice that we didn't just pass the coroutine object to async. We actually invoked it right there inside async's arguments. The async function doesn't actually want a reference to the coroutine function. Async wants the generator that we saw the coroutine function return. The async function adds the new task to the scheduler whether it's called from normal code or within a coroutine, which means that anytime we want to run a code in its own stream of execution, we can use async to get it going.
Even now that we've added the coroutine to the scheduler as a new task, nothing happens. That's because the scheduler itself is not running. That's a problem easily solved. We just need to call either the run-until-complete method or the run-forever method of the event loop. Run-until-complete accepts a specific future as its parameter and returns the value of that future when it finishes executing. Run-forever, of course, doesn't finish executing until it's explicitly stopped, and so its return value is not of any great value. As the name implies, run forever causes the event loop to run forever, or at least until it's explicitly stopped by calling its stop method, while the run until complete method causes the loop to keep going until a particular future object is ready to provide a value. The return value from async is a future object, so it's easy to have the scheduler run until a particular task is done. This example runs two coroutines simultaneously, as two separate tasks in the same scheduler. Coro1 coroutine contains an infinite loop, so it will never finish, but the Coro2 coroutine not only finishes, it eventually calls the event loop stop method to force run forever to terminate. This example behaves in exactly the same way, except it uses run until complete to automatically stop the scheduler once Coro2 is finished, instead of explicitly calling stop. The code looks a little cleaner this way, so as a rule of thumb, it's probably better to only use stop when some sort of an error makes it necessary to dump out of the event loop. In both of the examples we've just seen, there's a line of code to set the logging level to critical. That's because the event loop issues an error message to the screen if it is stopped while there are tasks, such as Coro1, still running. In this case, we know it's still running and we don't care, so we suppress the message. It's usually better to wait for all of our running tasks to exit cleanly instead of just killing them like this, which is why the error message is printed. But in this case, there's no problem, so we just keep the error message from showing up. Regardless of how we choose to run and stop an event loop, once we're completely finished with it, we should call its close method. That closes any open files, network sockets, and other I/O channels that the event loop is managing, and generally cleans up after it. A good way to handle that is using the contextlib.closing context manager, which guarantees that the close method will be called, even in error situations. The close method should be called when we're completely done with an event loop, but that doesn't necessarily mean it should be called right after run forever or run until complete finishes. The event loop is still in a valid state after those calls are done, and it's perfectly okay to, for example, add some new tasks and start the loop running again. As you've probably noticed, async.io event loop objects fulfill basically the same role as concurrent.futures executor objects, from a programming interface point of view. That's not the only similarity. So, coroutines are created using the async.io.coroutine decorator, and there's a default event loop already set up for us. The async.io.async function lets us launch a new parallel task, and we can run the event loop either forever, or until we stop it explicitly, or until a specific process ends. In the next video, we're going to look at async.io's future class and how it's used. 6.3 Futures. Async.io's future objects look and behave pretty much like concurrent.futures future objects, but they're not interchangeable. They have subtle differences in behavior, and of course major differences in how they interact with the underlying system, which are completely different. And of course major differences in how they interact with the underlying systems, which are completely different. Still, each feature is a way of referencing a value that may or may not have been computed yet, and if necessary a way of waiting for that value to become available. We're going to take a look at how the async.io.future object is most often used, or several ways in which they are commonly used. And we're going to also study for a moment why iterators can be a trouble with async.io, and how the futures can help to solve that problem. We're also going to take a look at when we should be using coroutines and when it's sufficient to simply use a future. The most commonly used feature of a future is to wait for its value to be determined and then retrieve the value. For async.io's future objects, this is done simply by yielding from the future. That will tell the scheduler to pause the coroutine until the value of this future becomes available, after which the future value is sent into the coroutine as the result of the yield from expression. If the future represents a raised exception instead of a value, that exception is re-raised from the yield from expression. If we don't want to wait, we can call the done method to check whether a feature is ready, and if it is, we can call the result method to retrieve the value. So the syntax and semantics are a little different, but the basic idea of a future is the same in async.io and concurrent.futures. When we're working with async.io, we use future objects all the time in all the same places that we might in concurrent.futures. But there's one particularly important case where we use features that's unique to async.io. To understand it, we need to take another look at how async.io's coroutines are built. Specifically, we need to remember that async.io's coroutines
are a special case of Python's generator objects, which are meant to interact with the scheduler, rather than the normal looping functions. They certainly don't work properly when a for loop tries to iterate over them, and any generator that will work in a for loop won't work as a coroutine. Iteration is a big deal in Python, so how do we deal with situations where we want to, for example, iterate over values that were retrieved from across the network? The answer is that we write a normal generator to interact with the loop mechanisms, but instead of having it produce the real values we're iterating over, it produces futures. Meanwhile, one or more other tasks are busy filling in values for those futures, happily running coroutines under the direction of the scheduler. On the other side of the iteration, and back under direct control of the scheduler, we yield from the futures, retrieving the actual values as they become available. The scheduler's task objects are much more lightweight than operating system processes, but future objects are even slimmer. In the example we just saw, a new task was launched to calculate the value for each of the futures we yielded, but in a lot of cases it would be more efficient to modify the code so that there's just one task working on all of the futures. That only makes the code a little more complicated, as we see here, and it makes the overhead much smaller. This sort of paradigm can be made simpler still by using queue objects, as we'll see in the next video. Also, take note that even though the iter function uses yield from, it's not a coroutine. It's using that expression in a more standard yield from the values of this iterable sense. In the last two examples, we assumed a fixed and already known number of objects to be iterated over. When we don't know how many objects will be iterated over when iter is called, things get more complicated, because how many features should we create to represent an unknown number of values? Well, in this example, we've made the body of the iter function into a while loop, generating one feature each time through the loop and handing off the decision on when the iterator should stop looping to the fill coroutine. This pattern too can be written better using async.io's queue class instead of the list we're using here, but we're going to get to that in a little while, so it's not involved in this example. We have to be careful of doing things this way because even though it works fine for for loops that yield from the future one at a time, it goes very wrong when we try the iteration without occasionally yielding to the scheduler. Passing an instance of this version of the slow sequence into a list function, a constructor for example, will freeze and then crash the program, as Python tries to make an infinitely long list. That's because the filler will never be done, because the list function keeps asking for more values without giving the scheduler any opportunity to run. Depending on usage patterns, it's also possible to have features at the tail end of the iteration that never receive a value thanks to having been yielded by the iterator just before the filler decided it was done. That's not as big a problem as a freeze crash, but it's something to keep an eye on. There are ways to design around these problems too. For example, we could have the iterator produce features of fixed-size chunks of values, and check between chunks whether another chunk is available yet. Alternately, we could have the filler run ahead as fast as it can and have the iterator just loop over the items already loaded, with the understanding that iterating over the object again might later produce different objects. No doubt you can think of other options as well. There's no best practice in this case. We should just pick a paradigm that works for our program. So, futures are rather a lot the same in terms of functionality and their basic paradigm between concurrent.futures and async.io. Async.io allows us to simply yield from a future, to wait for its value to become available and to retrieve it. Apart from that, it behaves and looks very much like a concurrent.futures future. Coroutines are generators, so the iteration protocol can interfere with async.io's task scheduling. But we can avoid that problem by using as the thing to iterate over rather than the objects themselves. Futures have extremely low resource requirements. So, when we have a choice between writing a function that returns a future or writing a coroutine, it's better to choose a function that returns a future. However, there are times when a coroutine is necessary because it actually needs to do processing, and in those cases, we should not hesitate to use the coroutine. In the next video, we're going to look at the aforementioned queue class, along with other ways of synchronizing and communicating between tasks. 6.4, making asynchronous tasks interoperate. We're going to take a look at the async.io versions of the synchronization primitives we've seen previously, as well as at the other end of the process, of async.io's versions as completed and related functions. And we're going to take a look at async.io's version of a queue. All of these things are functionally very similar to the things we've seen previously, but are designed to operate in the context of async.io's multi-task, single-thread processes, rather than in the multi-processing context we've seen previously. The async.io package provides lock, semaphore, event, and condition classes that are pretty similar to the ones we looked at in the context of multi-process programming. They provide the same method names and fill the same roles. The important difference is that for async.io's versions, some of the methods are coroutines, and some are not. Specifically, in each case, the acquire and wait methods, if they exist, are coroutines that must be called from yield from. This is because they need to be able to pause until some specific thing happens, and only a coroutine can pause and hand off control to the scheduler. Having mentioned lock and the rest, I want to point out that while they are sometimes necessary, they are less often needed under async.io than they would be under concurrent futures or other systems which provide multiple streams of execution. That's because async.io scheduling is cooperative. It's only possible to switch between execution streams at yields, which means that if there are no yields within a critical section of code, it can't be interrupted. No other task can modify the same data at the same time, because no other task has the opportunity to run any code during that time. Thus, lock and such are only needed when a critical section of code does in fact use yield at least once. We've seen as completed and wait functions before, in concurrent.futures. Async.io's versions are coroutines, of course, but they're not that much different in how we use them. The wait coroutine still waits for a group of futures to end, with an optional timeout, and returns a list of futures that are ready and a list of futures that are not. The asCompleted function still takes a list of futures and produces in the order that the results become available. Then we extract the actual values from the futures with a yield from, and are good to go. In this code, there's no telling what order the results will become available, but each time a value does become available, it will be printed. Async.io provides some other interesting coroutines for collecting data from futures, particularly wait for and gather. The wait for coroutine lets us wait for another coroutine to finish, but with a timeout. The first coroutine on the screen right now calls another coroutine and collects its result. No timeout, no anything special. The coroutine is basically just a wrapper. The second one does the same thing, but if the called coroutine doesn't finish within 5 seconds, a timeout error is raised. The third one does exactly the same thing again, except it handles the timeout error and follows a different code execution path after that. Then there's the gather coroutine. What it does is take a bunch of futures and make a single future that will be done when all of the subfeatures are done, and result in a list of the subfeatures' results. This is rather similar to wait, except instead of being a coroutine itself, it produces a future which produces as its result the same thing that would have resulted from the wait call. There are a bunch of uses for something like that, but one very nice thing we can do with it is to use it to construct the future that we pass into run until complete. In effect, we're telling async.io that it should run until all of these futures are complete. Futures are great for communicating one-off values between tasks, and event objects are good for sending simple signals, but sometimes we want a more fully featured communication channel. Fortunately, async.io provides us with a queue class and a few variants based on it. Async.io's queue has both the put and get methods as coroutines, and we have to already be in a coroutine to call them, unless we were actually going to use the async function to launch them as separate tasks, which would be wasteful and pointless. However, the queue class also has methods called put no wait and get no wait that are not coroutines and can be called from anywhere. In our earlier discussion of futures, we noted that using a queue would simplify the job of making a class that needed to use both coroutines and iteration. That's thanks to these methods. The iterator can use put no wait or get no wait, while the worker coroutine can use put and get, and the code comes out both cleaner and more efficient. Async.io provides a couple of variant queue types that return their stored values in different orders. Instances of priority queue give back the smallest object they contain, according to the less than comparison operator, when we call get or get no wait. So if a priority queue contains 34, 2, 5, and 97, calling its get coroutine return 2, the next time you called it would return 5, then 34, then 97. A LIFO queue, on the other hand, always gives back the most recently added object. It is, in other words, a stack data structure. Async.io also provides a joinable queue class, which adds an extra join coroutine and a method called taskDone. With a little bit of extra work, using a joinable queue allows coroutines to pause and wait until the queue has been emptied by other tasks. So we have all of the synchronization primitives that we'd seen previously in other contexts, but since async.io's scheduling is not able to interrupt processes and has to wait for them to allow the scheduler to switch tasks, they are less necessary in some contexts. We've also seen that it's possible to make any task have a timeout, so it runs for a certain amount of time and it either finishes before that time or raises an exception by using the wait for function. And we've seen how to combine multiple futures into a single future.
That's it for intertask cooperation. In the next video, we're going to take a look at the feature which most often motivates people to use async I/O, network communication. 6.5, communicating across the network. So, we've covered how async I/O works, and a bunch of tools that can be used to manage the execution of multiple streams in the code. That's all great, but what about doing some actual I/O with it? The primary motivation for people to use asynchronous I/O is when writing network clients and servers, although that's certainly not the only possible use. So not only does async I/O make network communications efficient, it makes them easy. So we're going to look at opening a connection to a server and accepting a connection from a client on the server, as well as sending and receiving data in both directions. Here we have the code for a simple client-server pair of programs. They just read and write the same few bytes over and over, but they also serve to demonstrate everything needed to communicate across the network. There should be little about the client that is mysterious. It runs only a single task, which uses async I/O's high-level API to open a connection and then send and receive data through it. The server is able to handle many simultaneous connections at once. Because the start server coroutine we called launches a new task to run our serve coroutine each time a client connects to the server. Each task has the job of handling a connection for that single client, so the serve coroutine is almost as simple as the client coroutine. There's only a little bit of extra code to handle a connection reset error, which is the exception that gets raised if the client suddenly disconnects from the server, and a little more to handle the case where the request is an empty string, which the readline coroutine can only produce if the client has closed the connection in a less precipitous manner. In both cases, we want the server to stop worrying about that particular client, which we can do simply by returning from the client handling coroutine. The task running the coroutine finishes, and that's that. In the launch coroutine on the server, we called another coroutine called waitClosed. That pretty much does what it says. It waits for the server to be closed. Without that call, our launch coroutine would immediately terminate, and since we used run until complete, the whole program would terminate immediately afterwards. That would happen because start server launches off a background task and then returns, rather than managing the server directly. There's a low-level communication API that async I/O provides, but for the vast majority of cases, the lower-level API is unnecessary. Async I/O makes network communication simple. So let's just start the server and maybe a couple of clients and see what happens. So as you can see, it's running through the server loop and the client loop rather quickly. There's nothing really to hold them back except for the speed of network communications, which is not terribly slow, especially running on the same computer. But they work. They just send their data back and forth and keep track of how many times they've done so. A couple 100,000 times, no muss, no fuss, it works. Async I/O makes network communication ridiculously simple, at least in the common cases. We can use async I/O's open connection function to connect to the server, and we can use async I/O's start server function to create a server to handle client connections. If we pass a coroutine into start server, it automatically creates a new task to handle each client connection. If we pass a coroutine into start server, it automatically creates a new task to handle each client connection. In the next section, we're going to look at metaprogramming, which is, broadly speaking, having code that rewrites or reinterprets the code of our own programs. Section 7, Metaprogramming. 7.1, Using Function Decorators. We're going to look at what a decorator is and how to make one, how to add data attributes to decorated functions from decorators, how to wrap a function from inside of a decorator so that its parameters and return value can be processed, and how to make parametric decorators that accept parameters of their own. Metaprogramming is a blanket term for techniques where programs use program code or data structures constructed directly from program code as data to be manipulated. Python has a number of different features that can be thought of as metaprogramming, and in this video we're going to take a look at one of the most ubiquitous, function decorators. The basic definition of a function decorator is simple. It's just a function that takes another function as its input, does something with it, and then returns the result of its operations. The return value replaces the original input function, so the changes a decorator can make are potentially quite drastic. A decorator that doesn't change anything at all is a function that accepts one parameter and immediately returns it. Python has a special syntax for applying a decorator to a function, using the @ symbol. Using this syntax, we just write an @ symbol followed by an expression that evaluates to a decorator function. We put that on a line right before the definition of the function we want to decorate. This syntax means, as soon as you're done defining a function, call the decorator function on it, and then assign the return value of the decorator to the variable that would have contained the function. It's also possible to use multiple @lines before a def, in which case multiple decorators will be invoked. The decorator that's closest to the def will be called first, then its return value will be passed into the next closest decorator, and so on. Eventually, the return value of the topmost decorator will be assigned to the function's name in the containing scope. In this example, the variable foo ends up containing a of b of foo. One of the most common use cases for decorators, and in fact the reason they're called decorators, is to add attributes to function objects. These attributes can be used by code in other parts of the program to distinguish decorated functions from each other and from undecorated functions. This is easy to do. Inside the decorator, we assign attributes to the function just like we would to any other object, and then we return it. Then, elsewhere in our code, we can check for the attribute and respond accordingly. That's all well and good, and often quite useful, but we can do a lot more with decorators. For example, we can enclose the function in a wrapper that performs some computation before or after calling the original function. To do this, we want to define the wrapper inside the decorator. If you haven't seen this before, it means exactly what it looks like. The definition of the wrapper function is actually inside of the intsOnly function, so when intsOnly is called, it defines and then returns a wrapper function. Each time intsOnly is called, it defines a new wrapper function. When a function is defined inside another function, the containing function's local variables remain available to the inner function. That means that our wrapper function can use the func variable to refer to the wrapped function. In this case, the wrapper does some manipulation of the function arguments and then calls the wrapped function and returns its result. We imported and used a decorator called wraps in the last example. The wraps decorator's job is pretty straightforward. It makes the wrapper look like the wrapped function to tools like PyDoc and help. However, you may have noticed when we used wraps that it took a parameter. How does that work? If a function decorator always accepts just one parameter, and that's the function being applied to, where did the other parameters come from, and where did they go? The key is that the @symbol isn't followed by the name of a decorator per se, it's followed by an expression that evaluates to a decorator. So wraps isn't actually a decorator. Strictly speaking, it's a function that returns a decorator. When Python evaluates the function call expression, wraps returns a decorator function, which is then applied to our wrapper. If we wanted to modify our intsOnly decorator so that we could specify an arbitrary function that would be applied to all the parameters, it would look like this example. So now we have a function called only, which returns a decorator, and which in turn returns a wrapper, which calls the original function. That might look terribly inefficient, but in fact the only overhead comes from invoking the wrapper each time that we call the function. The outer two layers of code only run once when the function is defined. So decorators are just functions that take a function as their argument and return a function, or generally a function. The return value of a decorator takes the place of the decorated function, which is why the return value usually is a function. A decorator can add attributes to a function and return it, or wrap it and then return the wrapper, or even return something else entirely. Any expression that produces a decorator as its result value can be used with the syntax. So that's how to use function decorators, and a taste of the sorts of things we can do with them. In the next video, we'll take a look at another programmable syntax feature of Python that meshes nicely with function decorators. 7.2, using function annotations. Function annotations allow us to associate arbitrary values with the parameters and return value of a function. We can access these annotations from program code by combining annotations with decorators or other code that accesses the annotation programmatically, and we're going to see how to combine annotations with decorators to alter Python semantics. In the last video, one of our examples was a decorator that automatically passed all of a decorated function's arguments through an adapter. That's pretty cool, but what if we wanted each parameter to be handled differently? Sure, we could pass a whole bunch of adapters into the wrapper, but that becomes ugly and clumsy as we start dealing with functions that accept more parameters. What we'd really like to do is attach metadata directly to a function's parameters. The metadata could then inform the decorator of what it should do. Fortunately, that's exactly what function annotations are. This example shows off Python's annotation syntax. To associate a value with a parameter, we put a colon after the parameter name, and then write an expression. That expression will be evaluated when the function is defined, and the result will be stored associated with the parameter name. We can also associate an annotation value with the return value of the function by writing a > symbol after the function's parameter list, and then an expression which will be evaluated when the function is defined, and the result of which will be stored associated with the name return. All of the annotations are stored in a dictionary called _annotations, which is an attribute of the function itself. As we can see here, annotations are not type declarations, though they can certainly be used for that purpose, and they resemble the typing syntax used in some other languages. They are arbitrary expressions, which means that arbitrary values can be stored in the annotation dictionary. They don't have any meaning to Python itself, except that it should store the values, but they can have a great deal of meaning to our code. Annotations combine well with decorators, because annotation values make a good way to provide input to a decorator, and decorator-generated wrappers are a good place to put code that gives meaning to annotations. For example, let's rewrite that decorator from the previous video. We'll switch to using only keyword arguments, just to keep things relatively simple for the example. The adapted decorator encloses the function in a wrapper. That wrapper only accepts keyword arguments, which means that even if the original function could accept positional arguments, they would have to be specified by name once the wrapper has been applied. The wrapper also looks for adapters in the function's parameter annotations and applies them before passing the arguments into the real function. Once the function returns, the wrapper checks for the return value adapter and, if it finds one, applies it to the return value before finally returning. When we take a moment to consider the implications of what's happening here, it's pretty impressive. We've actually modified what it means to pass a parameter into a function, or to return a value. Let's take a look at another example. Sometimes one or more of a method's parameters don't require any processing except to assign them to an attribute of self. Can we use decorators and annotations to make that happen automatically? Of course we can. Let's say that if a parameter is annotated with a string, the value assigned to that parameter will be assigned to an attribute of self using the string as a name. And if the parameter is annotated with true, the attribute will have the same name as the parameter. If there's no annotation, or if it's not a string or true, nothing should happen. Again, for simplicity's sake, let's limit ourselves to keyword arguments. As we see here, annotations simplify all sorts of code-based manipulations of code. We're using basically the same techniques as the previous example, but we're doing something entirely different with them. We've been looking at decorators as the primary consumers of function annotations, but that's not necessarily the case. Any code that uses a function object might be written to benefit from annotations. That means anywhere we pass a function as a callback, we can potentially use function annotation data to make the code smarter about what it does with the function. Event handlers could be annotated with the names of the values the handlers want to receive. Dependency injection could be automated in a similar way. Constraint-based systems could be provided with the constraints that apply to each parameter. Probabilistic reasoning systems could be annotated with prior probability distributions. Parameters could be annotated with the proper user interface element to display in order to have the user input the parameter's value, and so on. The possibilities are seemingly endless. Before we wrap up this video, I'd like to point out one thing that may be helpful down the road. Our example decorators that worked with annotations were all limited to keyword arguments for simplicity. If you find yourself wanting to do similar things but needing to handle all sorts of parameters, the inspect module's signature function will simplify the process significantly. Annotation values are the result of arbitrary expressions that are evaluated when the function is defined. The double underbar annotations attribute stores in a dictionary mapping parameter names and the word return, which is not a valid parameter name and therefore won't overlap with anything, to annotation values. The meanings of the annotations are entirely up to the code that processes them. Python itself doesn't do anything with them except to store them. Annotations combine well with decorators, where a decorator applies a wrapper that processes annotations. And that's it for the video on function annotations. Next, we're going to look at class decorators. 7.3, using class decorators. We're going to see how to use class decorators to programmatically add, remove, and modify the attributes of a class, wrap a class in generated code, or even use the class as structured input data for declarative programming. Class decorators work in the same basic way that function decorators do. A class decorator receives a class as its only parameter, and whatever it returns replaces that class. The return value doesn't have to be the same class, or even a class at all, but it should be something that is meaningful when it's bound to the class's name. It's rarely useful for a decorator to return none. Also, like a function decorator, a class decorator can modify the attributes of a class, or enclose the whole class in a wrapper code. However, modifying the attributes of a class is effectively the same thing as modifying the class's source code, which means that, unlike with functions, a class decorator can actually alter the structure of the decorated code, not just wrap it. Modifying a class is straightforward. We just use the built-in getAttr, setAttr, and delattr functions, or hasAttr if we want to check for the existence of attributes. In this example, we see a simple class decorator that adds a getItem operation to a class while removing the setItem and delitem operations, so that getting an item is equivalent to getting an attribute, but setting and deleting are forbidden. While rewriting classes via decorators can be a powerful technique, it's not a complicated or surprising one, so there's not much more to say about it. We can also wrap up classes in their entirety. One common use for that technique is to replace a class with a factory function. Using a factory function as the interface to creating class instances lets us choose to return an existing object if there's one we think is appropriate, rather than creating a new instance. Calling a factory function means give me the right object for these parameters, rather than give me a new object for these parameters. Let's take a look at an example class decorator that replaces the class object with a factory function for instances of that class. We'll assume that any two instances that were created using the same parameters should actually be the same object. In this example, we're using a weak value dictionary to keep track of the existing instances of a class and what parameters they were constructed with. That doesn't have anything to do with the class decorators per se. Instead, we're doing it because we don't want the cache to prevent the instances from being garbage collected. That's a good practice whenever we make a factory function that keeps track of the instances it creates. Another bit of good practice that we're demonstrating here is that we've assigned the class itself as an attribute of the factory function. That means that code outside of the factory function can still access the class object if it really needs to. So let's take a look at our factory making decorator in action. Notice that the thing named unique is in fact the factory function that was created for the unique class rather than the unique class itself. The actual class ends up being named unique.type. Also notice that u1 and u3 are not just equal, they're actually the same object. u2, meanwhile, which was created with different arguments, is a different object. Now we're going to take a look at something really wild. The syntax we use for defining classes is pretty generic. It could be used to represent all sorts of structured data. So why not use class decorators to transform class definitions into structured data objects? But by doing this, we can achieve a sort of sideways declarative programming paradigm. For example, let's say we want to connect to a SQLite database, and we want to create some tables in it if they don't already exist. We can make Python's class syntax work for us as a convenient way of expressing that idea, as you see on the screen now. We want the usage to look something like this, where the class structure and attributes provide the information that's needed to construct and configure a database connection for us. The end result should be a connection object, which we can use to issue queries according to the Python database API. There are a great many details that are ignored or handled simplistically in this example, but it captures the general idea and it works. The class objects that Python creates automatically when it's evaluating these statements. The class objects that Python created automatically when it was evaluating the statements you saw in the previous example are used to provide structured data input to this decorator, called database, and then discarded. The database decorator returns an open Python database API connection, not a class of any sort. So class decorators are functions that take a class as their only parameter and return, usually, a class. A class decorator can add, remove, or replace class attributes. The return value replaces the original class, even if the return value itself isn't actually a class. Class syntax can represent a wide range of structured data, so with the right class decorator, we can use it for declarative programming. That's the end of our discussion of class decorators. In the next video, we'll look at metaclasses, which are another way of manipulating the semantics of classes. 7.4, using metaclasses. We're going to take a look at what metaclasses are, how they relate to class decorators and to classes themselves. We're going to see how to use the metaclass to change the way the class namespace works. And we're going to see about adding inheritable special behavior to classes. Like class decorators, metaclasses are a tool we can use to adjust the basic meaning of a class. In concept, though, they're very different. A class decorator takes an already created class and transforms it in some way. A metaclass, on the other hand, can affect how a class is created, how it behaves, and even how classes that inherit from it are created and behave. To understand metaclasses, we first have to grasp the idea that classes are objects, and more than that, they are instances of another class called type. Anytime we create a new class, we're creating an instance of type, unless that class has a metaclass. If the class we're creating has a metaclass specified, or it inherits a metaclass from its ancestors, then the new class is an instance of the metaclass, rather than being an instance of type. That sounds like we could change the behavior of a class completely by giving it an unusual metaclass, but actually all metaclasses have to resemble type, or Python wouldn't be able to use them properly. Most of the time, metaclasses are actually subclasses of type, which makes things simple. Alright, so what can we do with a metaclass? First of all, we can run code before the code inside the class block is evaluated for each class which is an instance of the metaclass. We do this by giving the metaclass a prepare method in double underbars, which should be either a class method or a static method because it will be called before the instance is created. The prepare method is passed the name of the new class and a list of parent classes, as well as any keyword arguments supplied by the user. The prepare method can do whatever it wants, but it should also return a dictionary or similar object that can be used to hold the class's attributes while it's being evaluated. We can pre-assign values into the attribute dictionary from inside prepare, so we can actually assign attributes to the class before it even exists. That brings us to the second thing metaclasses can easily control: the class's namespace. In the first example, we returned a dict instance from prepare,
So instances of this metaclass, the basic metaclass on the screen, use a normal dictionary to store the attributes while their code is being evaluated. But we can return any dictionary-like object from prepare. For example, we could return an ordered dict if we wanted to keep track of the order in which attributes are created, as is done with the ordered meta class on screen, or a default dict if we wanted all attributes to have a default value. We could even use a weak value dictionary if for some reason we wanted the class to not protect its attributes from being garbage collected while it was being evaluated. Offhand, I can't think of any use for that, but it's possible. Of course, those are just dictionary-like classes that exist in the standard library. We could also use a custom dictionary-like class, which would conceivably do almost anything. If we want a class that ignores the case of attribute names while its code is being evaluated, we can do that. There's a reason I keep saying while the code is being evaluated. After prepare is called, the code inside the class block is run, and it uses the dictionary that was returned from prepare as its namespace. But after that, the metaclass's new method is called. One of the things new needs to do is call type.new to actually allocate and initialize a chunk of memory to contain the class data. And one of the things that type.new does is convert whatever we pass it as the namespace into an actual straightforward Python dictionary. That means that if we want to retain special information that our namespace object knows, we need to store it somewhere later where we can find it, as is done with the register descendants metaclass and the ordered metaclass in the examples on screen. We can make whatever changes we want to the internals of the class once we've created the object using the new method of the metaclass. We can programmatically add, remove, replace, wrap, and otherwise manipulate the contents just as we could with the class decorator. We can also return something that isn't actually a class object at all, again just as we could with a class decorator. The difference, aside from a bit of extra typing, is that the subclasses of a class that has a metaclass will also inherit that metaclass, while class decorators are not inherited. That means that, using a metaclass, we can make our unusual behaviors inheritable. The register descendants example makes it so that any class that descends from the class where the metaclass was originally applied can find all the other classes that also descend from that ancestor, including the ancestor itself. For example, here we have the metaclass applied to the quadruped class. Horse and dog are both descendants of quadruped. And as you can see, they've inherited the special behavior of the register descendants metaclass, giving them access to the registry attribute, which contains a set of all of the classes descended from quadruped. So classes are instances of metaclasses, which is not the same thing as inheriting from a parent class. Normal classes are instances of a metaclass called type. We can specify a metaclass alongside a class's parents by using the metaclass keyword argument of class parameter list. Metaclasses usually do their work in the new and prepare methods, prepare being an optional method. Subclasses inherit their parent's metaclass, so special behavior defined by a metaclass is inherited. We're done talking about metaclasses, so let's move on to the next topic, context managers. 7.5, using context managers. We're going to see how to customize the behavior of with blocks by writing our own customized context managers. We're going to see how to create context managers in two ways. First, by using the context lib module's context manager decorator, and second, by setting up class instances with the proper protocol methods. Context managers are pieces of code that plug into Python's with statement. A with statement contains a block of code, and the context manager is able to run its own code both before and after that block is executed. And the code that runs after the block is guaranteed to run no matter what happens within the block. The Python standard library makes quite a lot of use of context managers. Open files can be used as context managers, which guarantees that the file will be closed at the end of the block. Lock objects can be used as context managers, in which case they acquire the lock before the block and release it after the block is finished. SQLite database connections can be used as context managers, allowing them to automatically commit or roll back their transactions when the block finishes, and so on. There are other examples, but we can already see how useful context managers can be. They simplify the code by combining setup and cleanup into one thing, and they improve the code by guaranteeing that the cleanup code actually gets run. So how can we write our own context managers? There are actually two ways. The simplest is to use the context lib.contextManager decorator on a generator function. As we see here, when we create a context manager this way, we can write it as a continuous piece of code. We can think of the yield statement as a proxy for the whole code block that the with statement contains. If that block raises an exception, it will look to our context manager code as if the yield statement raised that exception, and we can wrap it in a try statement to deal with the exceptions that might occur. A moment ago, on screen, there was an example of using an open file as a context manager, and that statement had an as block. A moment ago, we saw an example of using the file open command as a context manager, or rather the open file that was returned from it. And in that example, we saw the as clause to the with statement. The as clause lets us bind a value returned from the context manager to a variable accessible within the with block.
The as clause lets us bind a value returned from the context manager to a variable accessible within the with block. If we yield a value from our context manager code, that value will be assigned through as to the variable accessible in the with block. In this example, we yield a function that prints the word during. So the entire result of our context manager is to print the words before, during, and after, assuming that that function is called. And typos aside, we see that it does. We can also write context managers by adding the double underbarred enter and exit methods to objects. Any object that properly implements these methods can be used as a context manager, which is how objects such as open files and database connections are able to do double duty as context managers as well. Here's an example in which we create a specialized version of a dictionary which can serve as a context manager. Within the scope of the with block, we can read and write data through the object that we returned from enter, but those changes will only be applied to the main dictionary if the block exits without raising an exception. The return value of the enter method is used by the with statement for the value to assign through the as clause, just as the yielded result was in the previous example. The exit method needs to accept parameters that specify the exception type, exception value, and trace back if an exception was raised in the with block. If no exception was raised, those parameters will all contain none. If an exception was raised, we need to decide whether and how the context manager will handle them. In our example here, we decide whether to apply the changes to the main dictionary based on whether or not an exception was raised, but otherwise we ignore the exception. If we wanted Python to consider the exception to be handled, we could have returned true from the exit method. That would be functionally equivalent to catching the function with a try except statement in a context manager.const. That would be functionally equivalent to catching the exception with a try except statement in a context-lib.contextManager style context manager. And here's our transaction dictionary in action. As you can see, the first transaction was successful, and the result was committed to the main dictionary. However, the second transaction involved raising an exception, and the result was not committed. Now that we have a good grasp on the mechanics of context managers, we only have one more piece of programmable syntax to cover. So the with statement runs code before the block begins. So the with statement contains a code block, and runs code both before that block begins and after it ends, even if an exception was the reason why the block ended. Using the context-lib.contextManager decorator, we can create a context manager using a single generator function, again, simple syntax. We can also make an object into a context manager by giving it double underbarred enter and exit methods. In the next video, we'll change the way variable accesses work by using descriptors. 7.6 Using descriptors. We're going to see how to use descriptors to run code when an attribute is read, written, or deleted. We're going to see how to use the property decorator to create simple descriptors, and we're going to make a more complex descriptor class that handles network interactions and does other complex behaviors. Reading and writing variables is one of the most fundamental aspects of programming. Python's descriptors let us alter how it works. A descriptor is an object that is stored in a class and controls what it means to get, set, and delete a specific single attribute for any instance of that class. If we want that sort of control over multiple attributes, we just add a descriptor to the class for each attribute we want to control. Python's built-in property decorator provides a simple way to create a descriptor. The first foo method we wrote here tells Python how to figure out the value of an attribute called foo, which in this case just means fetching it from another attribute and printing it the value. The later two foo methods are decorated to make them into the setter and deleter for the foo attribute, which means that assigning a value to foo actually means calling the setter method, and deleting the foo attribute actually means calling the deleter method. Both methods are optional for properties. Leaving them out makes the attribute that the property describes into a read-only attribute. Properties simplify the construction of descriptors for a common case, but there are cases where we could use a descriptor that property can't handle well. For example, what if we were planning on making a class that represented remote data, and we wanted its attributes to push and pull data from the remote source? We could do that with properties, but we'd end up writing the very similar code over and over, implementing each attribute. It would be better to have a remote resource descriptor class, and just add a bunch of instances to our local stub class. Let's go ahead and do that as an example. Actually interacting with the network requires a fair amount of code, so it's a good thing we can avoid repeating it over and over. The remote resource class we have here has double underbarred get, set, and delete methods, which determine what happens when an attribute that is controlled by an instance of this class is accessed. The get method, perhaps surprisingly, takes two parameters: the instance through which the attribute is being accessed, and the class through which the attribute is being accessed. It's like that so we can handle both instance attribute access and class attribute access. When accessing a class attribute, the instance parameter is none. In our case, we just return the descriptor itself if somebody tries to access the attribute as a member of the class instead of as an instance member, which is a reasonable default in a lot of cases. The set method is passed an instance and a value and conceptually represents setting the controlled attribute for that instance to that value. Unlike get, it doesn't have support for setting a class attribute, so instance will never be none and we don't need a class parameter. The delete method is just passed an instance and represents removing the controlled attribute from that instance. Notice that none of the descriptor methods are told which attribute they represent. The assumption is that their self parameter will, one way or another, specify that. In our code here, we've chosen to pass the necessary information into the descriptor's constructor and store it as an attribute of self. But in other circumstances, we might use self or self's ID as a key into a dictionary stored in the instances to store per instance state for the descriptor, or use the instance as a key into a dictionary stored in the self. We can't just store per instance data as attributes of self, though. The descriptors are attributes of the class, not the instance, so their values are shared by all instances of the class that contain them. Once we have the remote resource class, creating classes that have remote attributes becomes easy, as demonstrated by our record class here at the end. So descriptors override the semantics of accessing a particular member variable. For many uses, the property decorator, along with the setter and deleter subdecorators, provide all the functionality that we need. We can also define descriptors as objects, giving them double-underscored get, set, and delete methods. Descriptors are themselves, however, are attributes of a class, not of the instances of the class, even though they override the access to instance variables. There's a lot of room for creating interesting descriptors, but we've covered everything you need to know to start working with them. In the next section, we'll cover unit testing. Section 8, Unit Testing. Testing is often something of an afterthought for programmers, because it tends to be laborious and annoying. Also, we usually have a high degree of confidence in our work, and testing it seems unnecessary. It's also a fact, though, that confidence is often misplaced. Source code is a complex and subtle language, and it's easy to make mistakes while writing it and not even notice. We all know this from experience. That doesn't make it any easier to make time for something that is laborious, annoying, and feels unnecessary. 8.1. Understanding the principles of unit testing. We're going to take a look at how unit testing can help us write better code in less time, the basic principles that allow that to happen, and what good tests can tell us about our code. So the first question of testing is, how can we do it in a way that doesn't feel like a painful waste of time? Finding a way to overcome that psychological barrier is the first step to creating a testing method that will actually work. For a lot of programmers, unit testing does that, by reducing the effort needed to run tests, integrating testing with the development process, and making the tests themselves visibly useful. A unit test is a single small chunk of text code that tests for correct behavior or a single specific flaw within an isolated small chunk of program code. There are reasons for each part of that definition. A unit test is source code because one of the secrets of unit testing is that we put as much effort of the testing as possible on the computer, where it belongs. The test code tells the computer how to perform the test, which allows us to perform the test often and easily. A unit test is small because a large test is almost inevitably testing more than one thing. If we want to test for more than one thing, we should write more than one test. A unit test only checks a single aspect of the program code, because when a test fails, we want it to tell us exactly what the problem is. A unit test only involves a narrow region of the program code, because when a test fails, we want it to tell us exactly where the problem is. If we write a collection of tests that follow these rules, they are a unit test suite. With the proper tools, we can run our whole test suite with a single command, and the output of that command will immediately tell us the status of our source code with respect to the tests. If a test fails, it tells us what we need to work on next. If it succeeds, it gives us a reason for our confidence in the code it tested. The availability of automated unit testing leads to a programming paradigm called test-driven development. The basic idea of test-driven development is that, since a failing test tells us what we need to do next, we should never write program code except to make a failing test pass. If all of the presently available tests pass and the program isn't finished, we add another test to the test suite, and then write program code to make it pass. Doing things this way ensures that there are tests covering most or all of the code, and that the tests are run often, which makes it very difficult for bugs and regressions to sneak into the code without being noticed. It also lets us break the development process down into a series of short-term goals, which produce visible result when we achieve them. This is psychologically useful because it makes the programming process feel more rewarding, and it's much easier to perform a task that feels rewarding. Further, debugging tends to dominate the time needed for a project, and test-driven development reduces the time needed to deal with bugs. So, applied properly, unit testing principles and tools help us produce better code, do it faster, and enjoy the process more. It's an all-around win. Unit tests pinpoint problems, highlight solutions, and help us decide what to work on next. A good unit test tests for a specific problem in a specific block of code. Running unit tests is easy, so we should do it often. Python includes a framework for automated unit testing, and we'll take a look at that in the next video. 8.2. Using Python's unit test module. We're going to look at how Python's unit test tests are structured, the assertion methods we can use to check for specific conditions in our code, and how to set up an environment for tests and to clean up after them. The unit test package contains a framework for performing automated unit testing. Most of that functionality is based around the unittest.testCase class, which we will inherit from to create our own tests. In the basic test example on the top left, we see the basic features of a test case in action: test methods and assert methods. Any methods we define in a class inheriting from test case that have names starting with the word test are assumed to be unit tests. In this example, that means the test addition method is a unit test, but if we added another method to the class called connect, the unit test module would not treat it as a unit test. A test case can contain more than one test, and should when those tests are logically related and require the same operating environment to run. Inside of our test addition method, which is a unit test, we used a method called assert equal to actually check that the result of the code was as expected. Test case provides a wide range of these assert methods, which test for various relationships between our results and what we expected. We've already seen the assert equal method. It checks whether two values are equal and makes the test fail if they are not. The assert not equal method performs the inverse operation, checking whether two values are equal and making the test fail if they are. The assert almost equal and assert not almost equal methods are for use with floating point numbers. The way computers handle floating point numbers means that numbers which should be exactly equal actually differ in their least significant bits, at least sometimes. For example, if we square the square root of 7, the result is not exactly 7. So assert equal will treat it as not equal. However, assert almost equal will recognize that the two numbers are the same for practical purposes. The assert greater equal, assert less, and assert less equal methods check for the ordering relationships between their arguments. The assert is and assert is not methods check whether the arguments are references to the exact same object. The assert is none and assert is not none methods are a special case of that, and check whether the single argument is in fact the constant none. The assert is instance and assert not is instance methods check whether the object in their first argument is an instance of the type in their second argument. The assert in and assert not in methods check whether the object in their first argument is a member of the container object in their second argument. The assert count equal method is interesting. If we want to check whether two sequences are the same, we can just use assert equal. But assert count equal is for when we want to check whether two sequences contain the same values, but don't care about the order. The method will cause a test to fail if any of the members of either sequence appears in any other sequence in a different number of times. So, if A is in the first sequence twice, it has to be in the second sequence twice as well, but we don't care where. Finally, we have assert raises, which functions a little differently because it needs to catch the exception raised by the running code. That's a situation tailor-made for a context manager, and that's what assert raises is. Used in a with statement, assert raises makes the test fail if the code inside the with block does not raise the expected exception. That can seem a little backwards, but it's correct. The test fails if the expected exception is not raised. Sometimes, raising an exception is the correct behavior. For example, passing none into the int constructor should raise a type error, and if it doesn't, that's a bug. I mentioned in passing that all of the unit tests in a test case class should share the same operating environment. What does that mean? That means that each of them expects any external data that they access to be in the same state. For example, in the shared env tests on screen, each of the tests accesses a particular file, and each of them expects to find the same information inside that file. In this example, we have two tests that both read and write the same text file. Both of them expect it to contain the same specific information when they start running. In other words, both of them have the same expectations about their operating environment. When we have multiple tests that share the same expectations, and they're logically related, we should group them into a single test case. Then, we give that class a setup method, which is responsible for making sure that those shared expectations are met, and possibly a teardown method, which cleans up any changes that the setup method or the tests may have left lying around on the system. The setup method is run before each unit test in the test case. So in our example here, which has 2 unit tests, setup is run twice, once for each of the unit tests. Similarly, teardown runs after each unit test. That way, the changes that one test might make to the operating environment are removed before the next test runs. The starting environment is the same for each unit test in the test case. So that's the basic mechanics of Python's unit test framework as far as writing tests goes. To run the tests, we just need to invoke the unit test module from the command line. We tell it the file name of the module we want to run the test from, and it finds the test case classes in that module, creates instances of them, runs all of their tests, and gives us a report of which test passed and which test failed. Each test is a method of a unittest.testCase subclass. Test methods should have names that start with the word test. Test case instances have assert equal, assert almost equal, assert not equal, assert in, assert not in, and many more methods that we can use to check for whether our tests pass or fail. If a test case has a setup method, it is called before each test. Similarly, a teardown method will be called after each test. There are even easier ways to run the tests, but we'll look at that after we examine mock objects, which is the topic of the next video. 8.3, using the unittest.mock package. We're going to look at what a mock object is and what it's for, how to make them, how to check whether they were used properly, and how to replace existing objects with mock objects. We've talked about how it's important that unit tests only interact with a small section of code. But how can we arrange for that when so many pieces of code interact with objects and functions originating all over the source tree or throughout the standard library? One answer is that we replace those objects and functions with mock objects. A mock object is a clever piece of code. It can pretend to be almost any kind of object or function, but instead of doing whatever the original did, it just records what is done with it so that we can check it later. Let's play with a mock object for a moment to begin to get a feel for them. We can access pretty much any attribute of a mock object without defining it ahead of time. The result is another mock object. Similarly, we can call almost any method we want without defining it ahead of time, and the result is yet another mock object. In this example currently on the screen, the only attribute we access or method that we've involved that is actually part of what it is to be a mock rather than just the mock pretending to be whatever it is that I'm imagining it is the method calls attribute there, which is a list of the method calls that I performed on the mock and its sub-objects. That by itself is enough to let a mock object replace a large range of the functions and objects that our tested code might interact with. We can go even further if we take the time to pre-configure our mock object. We can assign non-mock objects to a mock object's attributes, so that accessing the attribute provides a specific value instead of a generic mock object. We can also assign a customized mock object in place of a method so that we can make the mocked method act more like the original, but in a way that's controlled by the test. We do that by passing a return value parameter to the mock constructor, which tells the mock object that every time it's called, as if it were a function, it should return that value. If we want the mock to return different values each time it's called, we use a different parameter of the constructor, called sideEffect. We have to know how many times the test will call the mock as a function, so we can provide a return value for each call, but otherwise this doesn't present a difficulty. We can also make the mock object raise an exception by passing that exception as the side effect or as a member of the side effect sequence. That pretty well covers how to make a mock that can, in a controlled way, stand in for real objects in code while we run our test. However, to really support testing, we also need to be able to check the mock to see if it was used as expected. We've already seen the method calls attribute of the mock objects. We've already seen that method calls attribute that the mock objects use to track their interactions. But mock objects also have their own assert methods that are usually easier to use than accessing the method calls list directly. The most useful of the mock object assertion methods are assert called with, which checks whether the most recent call to the mock object was done with the specified arguments, and assert any call, which checks whether the mock has ever been called with the specified arguments. So we know what mock objects are for, how to create them, and how to check their record of what was done with them. That's enough for replacing the parameters of a tested function with mock objects. We can even replace the self parameter of methods. If we call the method via the class instead of a real instance. What do we do, though, when the code we're testing reaches out into the system on its own and accesses something we'd rather replace with a mock object? For example, what if the code we're testing calls time.time? That's where unit test mock's patch function comes into play. Patch is a context manager, and it can temporarily replace very nearly any object in any package or module with a mock object. Once the block exits, the real object is restored to its position. Something to be aware of is that patch doesn't replace every reference to the target object with a mock. It only replaces the single reference that we specify in the first argument of the patch call. In our example, any code that accesses the time function by looking at references in the time module will get our mock object. But if there was any code that had used from time import time to create a local reference to the time function, that reference would still refer to the real time function. If we want to patch the time function for code that has a local reference to it, we need to pass the path to that local reference into patch. Instead of patching it in time.time, patch it in example.time or local.time or whatever the current module is or the module that has the local reference. We're pretty much good to go with mock objects now. That means we know everything we need to write powerful tests easily. So a mock object is a stand-in for another object. They help us keep tests from interfering with each other or from spreading out into the code that they are not supposed to be testing. Mock objects record what was done to them, so we can check it later as part of our testing. And unittest.mock.patch can temporarily replace another object with a mock object. All we have left to do is to find out how to run our test suites, which is the topic of the next video. 8.4, using unit test's test discovery functionality. We're going to look at unit test's ability to find tests to run automatically rather than being told which ones to run. We're going to see how to control that search, and we're going to look at a few things to keep in mind when we're using this capability. We've seen how to easily run all of the tests in a particular file, but for a large project, putting all the tests into a single file would be troublesome. They need to be separated into different files according to logical groupings, or the test suite becomes unmanageable. On the other hand, it would be a pain to have to manually tell unit tests to run the tests in a whole bunch of files, if we had to list each of the files one by one. Fortunately, there's a way to have our test suite split up into many files and still run it with a simple command. We use a unit testing tool that supports test discovery, which basically just means that it looks in the available files and decides for itself which ones seem like test files, then loads the tests from those files and runs them. The unit test module has a basic but useful test discovery tool built in. When we use python-m unit test discover, it searches the current directory for Python modules whose names start with the word test. In addition, it recursively performs the same scan on any subdirectories that contain an init.py file. Once it's collected the names of all of the matching modules, it runs the tests just as if we'd specified the modules on the command line ourselves. There are a few command line options we can use to adjust the behavior of unit test discovery. The first, which we saw in passing a moment ago, is the -v switch, which makes the test report somewhat more verbose. We used it here so we could see that the discovery had worked properly. We can use the -p command line option to change the pattern that is used to recognize test files. Here we've changed it so that the file names ending in the word 1.py are recognized as test files. The unit test discovery code also recognizes -s to specify the directory where the test search should start. Notice that by making the suite directory act as a starting directory for the search, we've stopped it from being recognized as a package containing the tests. If that's a problem, we can supplement the -s option with -t, which tells unit tests where to find the top-level directory for this run. By using both -s and -t, we're able to narrow the test search to a particular subdirectory, while still running the tests in the context of the parent directory. There's a bit of a pitfall to be aware of when using unit test discovery code, or any other test discovery code that works by importing modules to check whether they contain tests. That pitfall is the modules are imported. Most of the time that's not a problem, but if the test discovery code imports a module that was meant to be a program entry point, that might result in actually running the program, which is not the desired behavior. It's easy to avoid this problem when we're writing an entry point by wrapping the entry point code in an if name equals main statement. But if we or somebody else left off that check, and unit test thinks that file looks like a test file, running unit test discovery code will have surprising results. That's about all there is to the unit test discovery tool. It doesn't have many features, but it does have the features that everybody needs, and there's a good chance that it's all we'll need for the majority of projects. The discovery process will find test case classes, as long as they're in appropriately named files. The start directory, top-level directory, and pattern command line options let us configure how those files are found. And it's important to keep in mind that the test discovery code will import every module that it finds that has a name that seems like it might contain tests. That means that if any of those modules is the program entry code and it doesn't use the if name equals main trick, we might end up starting the whole program running rather than just importing for testing. For cases where we need more from our test discovery tool, we can use nose, which we're going to look at in the next video. In 8.5, using nose for test discovery. Nose is a fully featured third-party tool for test discovery and test running. We're going to look specifically at its code coverage plugin feature and how to run multiple tests across multiple processes to take advantage of a parallel processing environment. Nose is a third-party tool available via pip and the Python package index. It does basically the same job as unit test's discover command, but it supports a great deal more control and customization, as well as recognizing a wider range of tests. We're going to look at two specific features among the many that Nose provides. It can generate a code coverage report to tell us how much of our code our tests actually tested, and it can run tests across multiple processes, allowing them to execute in parallel on multiple CPUs. In order to get a coverage report, we first need to make sure that the coverage module is installed. We can do that with a simple pip command. Once we have the coverage module in place, we can enable coverage report for our tests with nothing more than a couple of nose command line options. Strictly speaking, only the with coverage option is required to enable a coverage report, but if we don't include cover erase as well, coverage data from previous test runs will get mixed in with our current run, which makes the results harder to interpret. There's a third coverage-related command line option that's sometimes useful. That is the cover package option, which narrows the code coverage report to only a specific package. Focusing the report in this way makes it easier to read and extract useful information. The other nose feature we're looking at here is the ability to farm out tests to multiple worker processes, and thus spread them across available CPU cores. To do that, we just have to provide the processes command line option, and tell it how many processes to use. If we pass -1 for the number of processes, it uses the detected number of CPU cores, which is probably what we want anyway. So unless we have a specific reason to do otherwise, we should always just use -1. However, as you've just seen demonstrated on the screen, the farming out of tests through multiple processes can sometimes cause surprising things to happen. In this case, combining it with code coverage, which I forgot to disable, produced the errors. The code coverage module is not compatible with being split across multiple processes simultaneously. And since I have it turned on by default in my system's configuration, it tripped me up. Having now disabled the coverage tests, you can see the multi-process test running. If you look carefully, you may have noticed that the suite actually took longer to run as multiple processes. That's because the tests themselves are very low effort, but launching a worker process is not. Fortunately, that's a fixed cost, so when we start running a larger test suite containing more expensive tests, we start to see benefits of parallel execution. This was just a taste of some of the features that Nose supports, and that's without writing our own Nose plugins to customize it further. It's a very capable system. So if we find ourselves needing a particular feature from our test runner, a good first step is to see if Nose already has it. So Nose looks for the word test to find tests, but it can recognize them in places where unit test wouldn't, like for example, the word Nose test, with the test as a later segment of the name. If we use the with coverage and cover erase command line options, we can get a nice coverage report for our tests if coverage is installed. Meanwhile, the processes equals -1 command line option lets us split the test suite across multiple available processor cores.